With the growing discussion of nuclear power around the world, it's important to be able to have an accurate understanding of risks and benefits and a real understanding of what radiation means to us from a health standpoint. And it's not just nuclear energy. There are many industrial chemicals and other substances that have varied regulations between different countries by orders of magnitude. This takes us to an issue of economic importance, but also of scientific importance, of how do we understand the world around us. I'm Jason Ross. This is March 30th, 2023, and I'm very happy to be interviewing again Professor Ed Calabrese. Ed, welcome.
Thank you very much, Jason.
So let's start with a brief biographical sketch. Could you please introduce yourself to our viewers?
Yes, be happy to do that. I'm a longtime university professor of toxicology within the School of Public Health and Health Sciences at the University of Massachusetts at Amherst. Been here basically since 1976, so I've pretty much seen it all in terms of the birth of environmental regulation in this country. Had the chance to write a whole series of books from probably 1978 throughout the decades. Been on a series of major National Academy of Sciences committees dealing with how do you establish safe drinking water standards on all kinds of agents, non-carcinogens, carcinogens, radiation, things of that nature. I was on the National Academy of Sciences committee that actually ended smoking on aircraft. And so that's, if I were to say one thing I was most happiest with was that.
Boy, you made a lot of travelers happy too.
I tend to think so. And variety of other types of committees and advisory boards of a national or international manner. And as it turns out, I have taught toxicology and risk assessment at this institution for really almost 5 decades. So I'm basically probably far older than I look, but you can, it's been a long time, but I've been able to know all the players and know the issues and the scene and been a part of that. But as it turns out, at least from a personal biographical perspective, something I used to be, when I was young and trying to make it in my career, writing books every year, doing all this laboratory research, trying to advise, you really enormous professional energy is in that stage of your career. And you're also trying to see where you fit in, trying to make sure you fit in, trying to make sure you get the right appointments, trying to please the people that are on top to give you those appointments. And I would have to say I was a golden boy in many ways as a very successful young academic, success beyond my wildest dreams, and enjoyed it all actually. And I picked up and learned the ways of the academic world and the regulatory world, and I understood that the nature of risk assessment and the nature of cancer risk assessment. And I understood what the federal government had bought into, which was a linear dose response paradigm, which was essentially going to judge chemical carcinogens and ionizing radiation in a manner such that any exposure to a carcinogen, even down to a single chemical or a single ionization, was viewed as problematic because they had adopted in the mid-1970s officially the linear non-threshold dose response. So all my textbooks, I actually was supporting an LNT model. I was part of the team, you might say. And then something happened to me along the way, and that is that I began to question the scientific legitimacy of that particular perspective, especially as we became much more knowledgeable about things such as how biological system cells repair damage, all kinds of damage, especially mutational damage, and also not just repairing damage, but how cells can protect themselves, and even before the damage begins. And so I began to look at, when you look in the mirror, and you see that, what really characterizes life is that we're survivors. We actually are survivors, and that we are challenged all the time, and essentially we're not. And when we get hit, we push back, and when we get cut, we heal, and we're not actually victims. And I began to think in terms of, what is this LNT model? What is the regulation? The regulation saying that any exposure to a carcinogen causes damage that's going to be problematic, predicts your cancer risk. And I said, well, wait a minute. What about this idea that, we wouldn't be here if we didn't repair damage? We'd have been dead a long time ago.
Right, right.
And we wouldn't be survivors. I mean, we're not actually sissies in this world. We're actually pretty tough creatures. And it's not just humans that are pretty tough creatures. I mean, you look at the tomato plant that might be growing out in your garden this year, or a turtle, or anything that survived all these years in this environment. So I began to see life very differently, and I began to question the basic methods that were used, or even the intention behind the methods. It may even be a good intention, but it's actually, a good intention that's actually wrong is going to lead you astray. And it could have all sorts of implications. And so I began to self-doubt, and then I began to question, and then I began to look at alternative models. And the next thing, that I was actually entering into a phase where I was challenging the belief system, the challenge and the framework. And that's really been where the last 30 years have led me into this. It's been a lot of fun, actually. It's fun to pursue truth.
What a journey, and what a great outlook. So you're going to be taking us on a tour, I believe, of this path of discovery. Let me just ask, as we jump into it, you had mentioned a couple of times linear no threshold. Let me just make sure I understand that right, also for our viewers. That's the idea that based on, if there's some substance where a lot of it kills you, then 1/1,000,000th of it will reduce your lifespan by 1/1,000,000th, or something along those lines.
Yeah, that's
there's no safe amount of anything that could become toxic at a high dose.
That's correct.
Okay.
It's even, you might say let's say from a smoking point of view, everybody accepts the fact that cigarette smoking is harmful, that it can cause a variety of types of cancers, including lung cancer. And you might say, well, epidemiology might associate that with let's say a pack a day, maybe a half a pack a day, for so many years. And you might say, at least from a LNT perspective, oh gee, I remember when I was in the 8th grade, I snuck a cigarette from my father. So a little pack of cigarettes. And I took, for example, let's say I took one drag on a cigarette one time. Now the LNT model would say that you increased your cancer risk by that one drag, that one time. And worse than that, my friend who was with me at the time I did it got exposed one time to secondhand smoke. So that person's exposure had very limited exposure, but LNT would say that person's exposure also put them at enhanced risk. You can carry this, down to a very logical, illogical extreme, where you can say that, one time to one molecule, according to LNT, increases your risk. And this is what the whole framework is ultimately based on.
So, well, I know you could destroy your liver with Tylenol. Does that mean that taking a Tylenol when you have a headache is partially destroying your liver? I mean,
Well, in that particular case, the argument would be, well, we think Tylenol might act according to a threshold. But when it comes to, and so therefore you might be able to have a certain level of Tylenol before damage occurs. But when it comes to something, at least from an EPA point of view, where you are exposed to a genotoxic mutation,
A
genotoxic.
genotoxic, meaning like that means
Yeah.
causing cancer potentially, or
Yes, that's right. That's the belief, is that there's this
hmm,
connection, direct connection, bingo, from mutation to cancer. That's how it was framed back in the mid 1970s. And so if you have a genotoxic carcinogen and you cause damage, then you ultimately set yourself on this path for carcinogenesis.
I see.
And it's basically thinking that in fact you can't repair that damage, and that it
Right.
and that it causes this change in this one cell, and that cell then, what they might say, clonally expands and then ultimately evolves into what we might call a tumor, something of that nature. But it starts with a very could start, according to the theory anyways, with a very tiny change that doesn't get repaired, and then that sets forth on a process. And 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 this is what I've set forth to explore.
Hmm.
What is the actual nature of the dose response in that low dose zone? Does it really follow a linear dose response? And I'd have to tell you that not only doesn't it not follow a linear response, but in fact, what really happens, based upon 30 years of study that I have put into this, and that is that the body identifies the damage, activates repair mechanisms. Those repair mechanisms go into operation. And the interesting thing here, and that people might find this comforting, and that is that there's a little bit of a overcompensation. When you sense damage, well, you want to produce enough protection so that you get rid of that damage that you have, but you want to do a little bit more than what you have, just to ensure that you're going to get rid of that protection. So it's like, I have a doctor's appointment at 10 o'clock. I think I'll arrive at 9:45. I don't want to be late. So if I have you have a little safety factor, 15-minute safety factor. Well, I have a mutation. I'm going to have to try to clean that up and repair it, but I want to make sure that I get it. So I'm going to rev up a little bit more than what I need. And so not only does it clean up that damage, but it also then takes care of some other damage that was from background activities. And so what happens is, as a result of that low level exposure, what you end up doing is actually showing not a linear dose response, but a J-shaped dose response. So a little bit actually induces what I call an hormetic dose response. And that is that you might see what amounts to some sort of protection or benefit
Hmm.
at that low dose. And I see that occurring for carcinogens, for non-carcinogens. I see that for all kinds of stresses that we have. And that is a basic way in which we actually are here today. And that is that our species are here today. They have evolved ways to enhance their capacity to survive
Hmm.
all sorts of circumstances. And it plays out in this low dose zone. Now, species that didn't develop that, well, then guess where they are? They're not here today, but the survivors have. And actually, this is how it plays out in the process of life. And we have these pretty amazing inducible mechanisms. And what you really find is that regulatory agencies decouple their philosophy of a protectionist precautionary principle, being fearful of danger, and they decouple it actually from knowledge of biological evolution, knowledge of adaptive responses, and they come up with a distorted picture of reality.
Hmm.
Ultimately leads to incorrect regulatory practices, and it comes up with wasteful spending, and also it comes up with ways it ends up hurting public health and the environment. It's amazing. And you might say, well, how could these very brainy people, and I mean, we have very brainy people who are in charge of our different organizations. I mean, people who the best educated, the best trained, they talk to each other, they get advice, and yet guess what? They got this wrong, and they've misled the country. And so how could leaders in this country, but not just this country, all throughout the world, all the World Health Organization, all the European countries, the Asian countries all buy into it. And they all have bought into a mistake that they have,
Wow.
the imprimatur of the scientific community is science, having been trained as a scientist, the one thing that I really loved about science and still do is that science is self-correcting. I mean, it's supposed to be self-correcting.
Supposed to be, yeah.
You're into, somebody does something and shows something. Well, I'm going to see if I can reproduce this, right? I'm going to see, or maybe do it better. And so you really compete with each other to try to figure out what's correct. And that's how we tend to move forward as people compete. But the interesting thing is when you look at what I call regulatory science, the science of the US EPA, guess what? It is not self-correcting. They have adopted a quote unquote scientific view back, in the 1970s, soon after they were created. And that view was, as I will talk about today, was very improperly put together, to be very polite. And this was adopted by the US EPA without scrutiny. And as all the information is piled up against it, it just doesn't seem to be capable of being corrected by a regulatory agency that I believe has decoupled their public health precautionary principle from what I earlier laid out, which was really an understanding of evolutionary biology, the concept that we're not victims, the concept that we actually can repair damage, all kinds of damage, and that we do. Okay. And that it ultimately affects our response at low doses, whereas the US EPA, they have viewed our citizens of this country and the citizens of the world as true victims. And victims that need their protection.
Right, fragile victims that anything can harm. Well, I understand that you've got some slides and things for us to take us on this journey. Let me just mention, just as a sort of a side note, that I wonder, I think some people hearing you talk about low doses might conflate that with homeopathy, and I'm sure you'll get into that later, but just to be clear, you're not talking about basically non-existent or homeopathic doses, right? You're talking about measurable small doses.
Everything I talk about is measurable.
Okay. All right. Okay.
A standard framework. Now, although later on, if you want to question me on matters relating to homeopathy, be happy to do that, because I've had to address those kinds of questions in many different fora as well. So I'm pretty familiar with that, the historical origins of it, how it compares and contrasts with current what I call biomedical science, and things of that nature. And we'll probably get into questions as, really, what is a low dose, and how and what does that really mean for regulation, things of that nature. So I'll bring some of those things up.
Good.
Yeah, but I'll begin to share my little slideshow at the present time. Okay.
Sure. Let's jump in.
Okay. Thank you very much, Jason. Appreciate it. What I'm going to talk about today, and have been a little bit in the introduction here, is the historical foundations of the LNT cancer risk assessment model. My presentation today is going to deal with the historical foundations of the LNT cancer risk assessment model. Now, what I'm really going to talk about, though, is I'm going to talk about how LNT was born, how it was created, actually created, and equally important, how it has been sustained over these many decades and in several generations of scientists. And I think the audience may be surprised to hear that this is going to be, it's going to be a scientific story, but it's going to be a story of mistakes and deceptions and failed public policy. It's hard to believe, it's going to be hard to believe that our cancer risk assessment policies and applications that we see carried out by the U.S. Environmental Protection Agency and similar groups across the world is actually based upon mistakes, deceptions, and failed public policy. Now, this historical outcome is really, when you talk about science, science is actually made up of and done by people, real scientists, and I have a listing of people who played a key role in making this happen from the early days to the present time, listed up here. And I want to show you, who these people are, real people that I'd have to say everybody who was on that list. They're highly accomplished. They are highly trained. They're extremely accomplished. They're made great contributions in many ways to society. But I'm going to share with you in this central area of cancer risk assessment, where they really have gone off the rail, where they've made mistakes, where they've covered up these mistakes, and it's part of their legacy. It's become part of our history. And so it's important to see who these people are and how they think and why they made these decisions that I'm going to challenge. Well, the person who has the most influence, the longest reach, the biggest name, the one who just doesn't go away, and that's Herman Muller. You can see him pictured here, probably about the age of 55. And you can see Muller here. He's a short guy in the picture, getting the Nobel Prize in 1946 from the King of Sweden. And this winning of the Nobel Prize, given Muller's ideology and perspectives, gave him a global platform in which to educate the world towards his biases. Okay, and Muller had enormous energy and intellect, and I have read thousands of his letters, and I can tell you Muller was just an engine, a little motor that would not stop working. He's an amazingly impressive individual, and I could tell when he was consulting for the federal government that he was always tried to do outstanding work, always in great detail. Muller was a very, very formidable ally and an equally formidable opponent. An amazing sort of a man. Here we have a colleague of his, Kurt Stern, who came from Germany to the United States, to the University of Rochester, and was a major player in the Manhattan Project. Now, you might think that the Manhattan Project was just about developing the bomb, with Oppenheimer out in the desert in New Mexico and things of that nature. But there was another component to making of the atomic bomb, and it was to evaluate the genetic effects of radionuclides. And this was done in large measure at the University of Rochester. And one of the key people directing this was none other than Kurt Stern. And Kurt Stern and Muller were very close friends and associates. We'll talk more about that. Here is Warren Spencer, who was a professor at the College of Worcester, a small college in Ohio. And he was a PhD from Ohio State in Drosophila genetics. And he was recruited during World War II to work on the Manhattan Project and plays a very critical role. You see him at a young professional stage here. Another similar sort, who was a parallel person to Warren Spencer, was Ernst Caspary, another European transplant. And as it turns out, in the studies that went on with the fruit fly, Spencer was doing what they call short-term acute studies, whereas Caspary was doing low-level chronic studies over the entire lifespan of the animal. Here we have Delta Uphoff. Delta was a first-year graduate student at the University of Rochester who took over for both Spencer and Caspary to try to replicate their findings. And she had a very significant role in the final disposition of LNT. Warren Weaver, he was the director of research for the Rockefeller Foundation. And he plays a significant role because the Rockefeller Foundation ultimately provides major funding to the National Academy of Sciences to evaluate all things radioactive or all things nuclear. And he becomes the chair of the most significant genetics panel, and he'll really affect how regulations go forth in this country. But that's Warren Weaver. And Weaver was not a geneticist. Weaver, that's very significant here, but he's going to chair the genetics panel. He's a mathematician, but he knew all the geneticists because he funded their work through the Rockefeller Foundation for many years, and salaries and all sorts of their operations. He knew where they stood on every issue. Over here, this is the only person in that era, the era of the 1940s, 1950s era, where advice was coming forth from these genetic panels that I got to know. And this was James Crow, Jim Crow. He was a University of Wisconsin professor. He went to graduate school to study with Muller down in the University of Texas, and Muller actually left just at the time he arrived to take a Fulbright in Europe, and he never actually worked with Muller at Texas, but they became very close associates over time. And my interactions with Crow may be of interest to the audience, and that was that when I started to be very critical of Muller and this whole process, I wrote an article that was highly critical of Herman Muller, and it was around 2012. And I wanted to know what Jim Crow thought about it, because Crow and Muller were close. And I knew that Crow was 94 and a half years old then. And so I said, oh gosh, I wonder how he'll respond to this, if he'll respond at all. So it was in early February, I believe, of 2012. And it was at the halftime of a Super Bowl game in which the New England Patriots were playing. And so I had this manuscript, and I said to my wife, I said, I'm going to go and email Jim Crow at the halftime, and I'm going to see if he'll read my paper about Herman Muller. And so I ran to the computer and typed a little note to Jim Crow. And then within 3 minutes, Crow writes back to me and says, Ed, send this along. I'd love to read this. And it began a letter writing relationship that I had with Crow. And I got to know his opinions of my paper, some other papers, and his views. And Crow would die, within a year or two later. But it was my and I've saved all my emails from Crow. They're kind of an historical little document. But Crow was a very loved man within his community, highly regarded. And you can just see, well, he's got a nice, friendly, beautiful, friendly face. He's a warm professor. Over here is George W. Beadle. And Beadle is another Nobel Prize winner like Muller. He gets it in 1958. He was on this committee that Warren Weaver directed, the National Academy Committee on Genetics, assessing genetic risks. And he's a very significant player. He's a Caltech professor. This over here is William L. Russell. And Bill Russell was from England, migrated to the United States, got a PhD at the University of Chicago, ultimately settles at Oak Ridge National Labs and becomes a major mammalian geneticist, radiation geneticist, whose work today has framed and shaped the cancer risk assessment for the United States and the world. He's a very significant player. This over here is Leanne Russell, and this is we got an older picture of Bill, but Leanne was his wife with a younger picture, and the two of them were a powerhouse genetics couple. So when I talk about Bill, I really can't separate him from Leanne. They were both major players. Over here, this is Louis J. Statler. Statler was a plant geneticist, radiation plant geneticist, studying corn, and he was at the University of Missouri, and he was in a race with Muller to be the first to induce gene mutation, and Muller beat him to the punch, and only beat him by 3 months, a mere 3 months, and because of that, in this country, whoever finishes first is wins, and who comes in second's the first loser, so to speak. But Stadler was really was close to 3 different Nobel Prizes, and he just missed getting any one of them, but he was a very major player. This over here is Barbara McClintock, and Barbara McClintock is perhaps the most creative geneticist, in my opinion, in the 20th century. She has a very significant role in this operation and challenging some of the thinking of Hermann Muller. This over here is Nikolai Rozovsky, and he's a Soviet geneticist, and he was a colleague ultimately of Muller, and played a very important role in the very first quantitative modeling for LNT. This is Max Delbruck, another Nobel Prize winner from the United States, but worked with Rozovsky to come up with the LNT single hit model, which was really based upon some of Delbruck's thinking on what a physicist would call target theory, and focusing in on the target of the gene. This over here is Edgar Altenberg, and Edgar Altenberg is Muller's alter ego. They were the best friends in high school, best friends in college, went to graduate school together, became professors in Texas. Altenberg's at Rice. Muller went to Rice first, and then to University of Texas at Austin. They were born within months of each other and died within months of each other. They communicated constantly, and I have all their letters in between them from the time they were very young to the time right at the very end of their lives. If you wanted to know the real Muller, you find it in the letters between Altenberg and Muller. If sometimes you have to play nice in public, for example, Muller did not like his department chair at the University of Texas and didn't have a high respect for this particular man. Yet this man had a good scientific reputation, and everybody thought that he and Muller got along quite well. And when he was nominated to become a member of the National Academy of Sciences, they asked Muller to give the introduction and welcome to his former department chair as he gets this great honor of being inducted in the National Academy of Sciences. And Muller writes to Altenberg and says, gosh, they've asked me to give the introduction to Patterson, and I have to do this. And if anybody doesn't deserve it, it's him. He is not a competent scientist. He said, I'll just go there and lie and tell them what they want to hear. And they'll think that he and I are the best buddies in the world. And so I'm saying, wow. I said, on the outside, everybody thinks that Muller and his old department head are close friends, but the reality was actually seen in the letter of Muller to Altenberg. And so when you read these letters, you get to see the human side of this, and sometimes a deeper reality into what's actually going on in the dynamics as compared to the political niceties that you see in social interactions. And so there's a lot that goes on like that. James Neal, he's a University of Michigan professor who was very important because he was recruited early on, right after the end of World War II, to become the person who was going to be in charge of the major human study to take a look at the effects of the atomic bomb blast on the offspring of adults that were exposed to the radiation from the atomic bombs. And Jim Neal follows this from really 1946 until his death from prostate cancer in the year 2000. And he has a very interesting, troubled, dynamic relationship with Muller. We'll know more about that later. Over here is Marcia McNutt, and Marcia McNutt is the current president of the National Academy of Sciences. And just before that, she was the editor-in-chief of the journal Science. So Marcia McNutt has had extremely high-profile positions within this country and scientific leadership, and is still in the National Academy presidency today. Now, these are the players, major players. There are other players, and some other names will come up, but I wanted you to see who these people are, have a feel for them as people, because they are real human beings. They have goals and aspirations, and they have their strengths and they have their biases and weaknesses, and none of us are perfect, and they're certainly not going to be claiming to be perfect either. And so we'll examine how it all fits together, and where there are tensions and where there aren't tensions, and where they work together and where they cannot possibly work together, and how that affected what we call LNT, or cancer risk assessment, today. Now, I want to make sure that you see that this is a historical process, and it's got a long history. This is a century in the making process, actually. We go back to 1927 when Muller makes his big discovery, reports his big discovery for the production of gene mutations in the Journal of Science. And then that discovery becomes the big key, because earlier in my discussions with Jason, I mentioned to you that cancer has been believed to start with mutation in a single cell. And then that cell, clonally expands, and lots of things happen on the way to develop the tumor. But Muller was the one who gets credited with showing that radiation can induce mutation. And that started the whole process. And then ultimately we see over the course of the years, you build upon that. By the 1930s, there was the creation of the single hit model, which was then donated to EPA 40 years later and used to establish some of our ways of assessing risk. We have World War II with the Manhattan Project, which is going to be trying to figure out how do we assess risk from radiation from low to high doses. Then the National Academy creates a committee called BEAR, which stands for Biological Effects of Atomic Radiation. And they make the recommendation to the country, and ultimately adopted by the world, to go linear. This is reaffirmed in the modern era by another national committee called BEAR, Biological Effects of Ionizing Radiation. And Jim Crow was on both of those committees. He held sway a long time. And this is ultimately then passed on to the EPA, who accepts the BEAR 1 recommendations, incorporates it into cancer risk assessment, and carries it right forward to the present time. Now, in this next slide, you can see I've kept the previous one together, but added some words written in red. And these identify some research developments that we'll talk about as we go forth in this story. Now, I'd like to now really focus in on the actual story itself. And it really goes back to Muller. And what we have here is, did Muller really induce gene mutation? And what I'm going to be telling you is that Muller actually did not induce gene mutation. Muller confused an observation with a mechanism. And in doing so, confused himself and confused the world. See, what Muller did was, Muller had tried, when he was a graduate student back in 1910, 1911, went to Columbia University to study with this gentleman, Thomas Hunt Morgan, who was a well-known professor at Columbia. And they were just embarking on this concept of studying, or could they induce gene mutation? Now, in today's world, we think, oh, it's so easy to induce gene mutation. I mean, they have journals on mutation research. They have all kinds of journals on mutations. You think it's chemicals can induce it, radiation can induce it. Lots of things can induce gene mutation. But back in Muller's time, they actually could not induce gene mutation. They working with these little fruit flies that grow on bananas and things of that nature that we all have some experience with, and they have some very prominent characteristics of their chromosomes that make them nice to study under a microscope. But they have visual characteristics which you can see. They have red eyes, and if the eyes change to white, then you might call it, maybe that can be identified as a visual mutation. They have other kinds of changes.
Ed, let me ask, so you said that at this time, people were unable easily to create mutations. What led to the hypothesis that mutation was a thing? Was it that in generations of these flies, you'd suddenly find a new characteristic that wasn't in the ancestral generations, or where did it come from?
Well, it really evolved from, in many ways, inspired by the work of Charles Darwin. Because Darwin came up with this, publishes his book in 1865, The Origin of the Species. And he's claiming that life evolved on Earth, and that and he didn't understand the mechanism of it, but he had come up with natural selection, and ultimately people thought that there had to be some sort of genetic material that was altered, that was then selected for, and those became the survivors. And then people began to try to understand soon thereafter, although it wasn't quite connected, there was the work of Gregor Mendel, dealing with his peas growing in the monastery garden, in which he could see the passing of traits from a tall or small pea plant, or one that had different colors in the flowers and things of that nature, and was able to see that the traits were actually passed on through reproductive organs of the plant, and that had certain numerical frequencies, and ultimately that led to the recognition that there were such things as they called, didn't understand them, but they were called genes that were passed from one generation to another. And then others began to take a look at this as well in some detail, and looked at breeding and crossbreedings and following traits and looking at variability, and led to different ways of trying to understand variability, mutation, what were the causes of it, and things of that nature. And it was very struggling, nebulous, from the 1860s to the early 1900s, and yet there was this great interest, because somehow the people who were the scientists of the day, they knew that there had to be a cause of evolution, and it had to be somehow something that had the capacity to alter the genes, and to mutate them, to change them in some sort of a fashion. And on occasion, they would see visual alterations that led them to know that something changed. We don't know what caused it. And in the historical story in Thomas Hunt Morgan's lab, that one of the workers there saw that the normally red-eyed Drosophila appeared white.
Mhm.
And they knew that a change had taken place, and so they wanted to save that creature. Could they breed that creature? Could they then study that more so? But they wanted to see, not that it occurred, but they wanted to see, could we make it occur?
Can we make it occur? Okay, I see.
Could we induce it? And so he attracted with his ideas, that's Thomas Hunt Morgan, some students, and Muller's one of them. And they go into the lab, and they try to treat these little fruit flies with everything that they think that might be harmful. And so they have very toxic chemicals. At the time, they knew that mercury was very toxic, that lead was toxic. They knew that arsenic was toxic, formaldehyde was toxic, other agents. And they gave these fruit flies the highest possible doses of these very toxic agents, and they were unable to induce mutation. They also, back in 1895, X-rays were first discovered. And so now they had, by 1910, they had the capacity to expose these creatures to X-rays. And they also had the capacity to expose them to some of the ionizing radiation that came from, let's say, radium, some of the radionuclides. And so they tried to induce it this way. And in every particular instance, they failed to induce gene mutation. Now, they sometimes they thought they had it, but they never really were convincing to themselves or to others. Muller got very interested in, well, could you induce it by heating them up? Could you induce them by cooling them down? Could you induce them by giving them, ether was discovered in the was it the 1840s, and ultimately used in anesthetics and things of that nature. And they would use ether to knock the mice out and knock the fruit flies out when they're trying to manipulate them and so forth. They etherized them. Everything that they could possibly do to these little creatures, they did. The intention of trying to see, can we induce mutations? Because if you could induce gene mutations, there may well, in fact, have been the possibility of winning a Nobel Prize. This would be like the major question. And so Muller was really very, very focused on trying to be the first to induce gene mutation and to try to make this actually happen. But he just could not make it happen. And it wasn't like, it was sick, he did this over 6 months, or he did it over 2 years. I mean, this is going on for over a decade. Picture yourself with a motivation to come up with a scientific answer that the question is eluding you for over 10 years and counting. And you're not the only one. And you absolutely know that because you have developed a belief in evolution, that there's an answer to this question, and it has to be at the gene level, but I can't figure out how nature did it. And I can't do it myself. And this is a very interesting situation. And so, and Muller's not the only smart person who's trying to do this. And Columbia is not the only institution where that work's going on either. It's going on around the world and in multiple places in this country. It's going on not just with fruit flies, but with plants, other biological organisms. You don't really know who's doing exactly what, how close they are to winning the prize, all this sorts of things. But Muller, what he does is he makes a strategic move that made the difference. And you might think that this was a sign of brilliance, and it probably was a sign of brilliance. But a lot of times when a brilliant idea or decision is made, when you look back on it 40 years later, you'd say, well, that wasn't so brilliant. But at the time, nobody else could figure it out except the person who figured it out. And that was Muller. And that was that one of the reasons why people couldn't quite agree on mutation was that they're looking at visual mutations. And the problem here was that you could see variability. You could see variability in wings and variability in the antennae and other features. But it was variability, and you couldn't quite tell, was it really normal, just variability that you might have guessed from like a Gregor Mendel sort of research, or was it really mutation? And one of the problems that they had at the time that I think the audience needs to appreciate, and that was that actually seeing mutations, visual mutations in these Drosophila was a very rare event. Now, Muller, he speculates based upon counts, but he says out of about 20 to 25 million fruit flies, I mean, I don't know how they ever counted them, but let's say, but he writes it down, out of 20 to 25 million fruit flies, they estimated that they had seen 400 visual mutations. That's about 1 in 50,000 fruit flies. It's very, very rare. Who could even count 50,000 fruit flies, right? To find one mutation. I mean, just think of the endurance of the laboratory person to look at 50,000 fruit flies to find one mutation, and to think if you had just dozed off for 5 seconds, you might have missed it. I mean, seriously, and because it was so rare, this is like the fundamental point here too. Because it was so rare, what happened is that Muller came up with the idea that in fact the genome was very stable. The genome was very stable. That means it wasn't susceptible to mutation, yet evolution had to occur because of mutation. Yet it was so stable. And so he knew that mutation did occur because they had seen these mutations. But then So what did that mean for Muller? Muller came to the conclusion that, gosh, mutations are valuable, but they're very rare. And I believe that led to him coming to the conclusion or excluding the concept of repair of mutation in his thinking, that if in fact there was such a thing as repair, then there may not have been enough mutations to actually fuel this process of evolution.
Let me just take a moment on that. So I'm just going to put our faces up for a second. So Muller, based on the fact that it was so hard for him to generate visible mutations, concluded that it must be exceedingly difficult to create them, and that since it's so hard to create them, if they were also being repaired, they would essentially never be able to cause changes in evolution.
That's correct.
And therefore, there couldn't be a repair mechanism, because otherwise there'd be no chance of getting mutations and change over time.
Okay, so what I want to discuss with you right now is really Muller and how Muller made his big mistake. And the big mistake was, why he thought that there was such a thing as a linear non-threshold dose response. And it was really two mistakes that he makes. And the first one was he really got the concept of evolution wrong, as we have kind of suggested. And then he integrated this mistake into risk assessment. Now, as discussed earlier, how does he actually make this mistake? Well, he makes this mistake because in his experience, and this is experience over a number of years, a decade or more, what became really obvious to everybody in the field was that there were very, very few visual mutations in fruit flies. Of 20 to 25 million fruit flies that they had estimated people had observed, they only saw about 400 visual mutations. It's very, very rare, 1 in 50,000. And so it seemed practically impossible to induce gene mutations, yet they did occur in nature. I mean, he did see, 400 out of 20 to 25 million, not very many. And so he concludes that this genome is extremely stable, very stable. Now, what does that really mean? That means that, gosh, how does evolution actually take place? And you can see Muller in this 1929 paper, how he, in sort of an amusing sort of a way, characterizes these observations and puts them into some sort of a perspective. So he writes, in the course of this work, animals and plants have been drugged, poisoned, intoxicated, etherized, illuminated, kept in the dark, half smothered, painted inside and out, whirled round and round, shaken violently, vaccinated, mutilated, educated, treated with everything except affection from generation to generation. But their genes seemed to remain oblivious. They could not be distracted into making an obvious mistake. And so that Muller's sharing with you, gosh, we tried to induce gene mutations. We threw everything at these creatures, everything except the kitchen sink. And they could not induce gene mutations. Very, very difficult to do. You'd think it was the easiest thing in the world to do. It wasn't. And so this is why, Muller's discovery in 1927 becomes so gigantic, because nobody else could do this. But he did. And it got the attention of the world. And Muller had induced these gene mutations with very high doses of X-rays, extremely high doses of X-rays. And yet Muller's trying to figure out what the cause of evolution is. And so he writes 2 years later that he's found at least one of the natural causes of mutations and hence of evolution, indicating that background radiation was a cause of evolution. Now, for Muller to make that claim, he had to do some fancy extrapolation work. And that was that Muller was actually exposing his animals to a dose rate of radiation that exceeded what I'm being exposed to and what Jason's being exposed to by about 100 million fold. I mean, it's a massive amount. The level of radiation that he gave those fruit flies, and fruit flies are very resistant to radiation compared to mammals, okay? Very resistant.
Mm.
But even the doses that he gave killed many of his fruit flies and sterilized most of them, but a few, a certain percentage make it through so that they can participate in the study. And Muller picked up on using this extremely high dose from some other work that was going on at the time, which was looking at the effects of very high doses of X-rays on something called crossing over between chromosomes, which you could induce to increase by about double with a dose that was sterilizing over 90% of the fruit flies in the study. Very, very high doses. So when Muller set forth to do his work, was Muller going to work with low doses of radiation? No way. No way. Muller set off right off the bat, choosing doses of radiation that were going to sterilize or kill a high percentage of his creatures. And that's what he did. Yet the very first thing Muller did was what? Muller said, we've found at least one of the causes of evolution, and it comes from what? Background radiation. Now, that meant that Muller was extrapolating his findings over what? Over a 100 million fold of exposure. Now, that's like saying, well, wow, I mean, if I'm concerned about, a chemical in a soft drink, like a dietary sweetener, right? And it causes, if the equivalent of 10 million cans of this particular diet drink causes cancer in rats, the equivalent thereof, then one would be a cancer cause. I mean, it's a massive extrapolation. It's in many ways like a person who's a weatherman trying to predict exactly what's going to happen 10 years from now. I mean, extrapolating way beyond your data to something into the unknown. What's going on the other side of the moon or something like this? It's very difficult.
And to be clear, that's because he didn't do experiments or successful experiments with lower doses. His only data was at a very high dose.
That's correct. His data was extremely high. And the reason why Muller made this break was, and this is interesting, other people were looking at this, but Muller decided to not look at visual mutations in a traditional sense of the word. This was like, eye color or the veins on a wing, this sort of thing. Muller knew that he really had to break the logjam, and that was he wanted indisputable evidence that he had induced gene mutation. And so Muller decided that there were genes that led to lethality in fruit flies that existed and would have existed in some sort of recessive condition, and that he needed to try to look at lethality as the endpoint that he was interested in. And he knew that some of those genes were on the X chromosome of the fruit fly. And so what he did was he decided to do what's called a sex-linked recessive study. And he was trying to see if he could induce fatal mutations in the male fruit fly. Kind of like, when we have a sex-linked trait in humans, it tends to be found predominantly in males, and we might have color blindness, things of that nature, that because the gene is on a certain part of the X chromosome that the female, we have an X and a Y chromosome. Female has two Y chromosomes, and if we have the mutation on the X, we don't have a dominant gene to balance it off on the Y because it's a shortened chromosome. So Muller used that concept, applied it to the fruit flies, and that's what he was actually doing in his work, because he did not want to get into debates over the shape of the antenna, the number of little veins in the leaf, because that was too subjective. But it wasn't subjective if the animals died. And so that he could take a look at were there males or there weren't males in the next generation. And so he looked at sex-linked recessive traits, and he looked at really visual presence of males or not, and he could determine whether there was a mutation or not by the presence or absence of males in the next generation. And so it made it very clear, and it was actually a very simple concept. It wasn't like he had come up with a new biological concept. He came up with a new strategy for trying to come up with the answer. And that's what led him to his grand discovery. But he did that with a dose rate that was 100 million times background. And he extrapolates that down to background radiation, which is extremely low, and making that think that that's actually very relevant to life. And so the big mistakes that Muller made then was that the genome itself is the genome is now known to be very unstable. Vast numbers of mutations occur every second of every day in each cell. It's hard to actually believe this, but this is what we've now learned, and that is that Muller's whole concept was totally wrong. He thought that the genome was stable, but there's so much damage that goes on, and it's repaired so quickly that you don't even know that there was damage there that was caused. It's a very interesting idea, and you could see how Muller would have been confused on this and could have made a mistake. But Muller's problem was that you could take a look at just picture yourself. You see 400 visual mutations out of 20 to 25 million fruit flies. Muller concludes, well, the only way that could have happened is that it's a very low rate of mutation. The genome must be very, very stable. Well, yeah, okay, I'll agree with him. That's a viable hypothesis, right? But you could say, I could still have 400 mutations out of 25 million if there was a lot of damage, but the system repaired most of that damage. I could still come out with the same 400 mutations. I just get there in a different sort of a way.
I see.
And what Muller did was Muller only proposed one hypothesis, that his was correct, but there could have been other hypotheses that could have been put on the table to be tested, but they weren't. And so Muller then had to somehow use his hypothesis to then apply it to the issue of LNT. And he said, well, since there are so few mutations, gosh, if we repaired them, we wouldn't have enough mutations that could actually become the driver of evolution. So he excluded the concept of repair from his paradigm. And that led him to ultimately fall into the trap of LNT and to not let it go. And so this was actually the original sin. This is the original intellectual sin for LNT. And it happens because Muller fails to propose more than one hypothesis and to test them out.
Well, let me ask this: if it wouldn't be purely speculative, and if it is, then just say so. But I don't know if from his journals or whatnot, if he had other ideas in mind, but was very eager to publish, and get priority in that sense, and therefore kind of let him go. Or do you have any thoughts on that?
Well, he was very eager to prove or to demonstrate that he had induced gene mutation. Absolutely, there. It was so. It was. This is. He raised an interesting point. He knew he was in a race, and he knew that there was even a group 6 months before Muller had published an article in the Proceedings of the National Academy of Sciences on gene mutation, claiming gene mutation with plants. It was a modest study. They had only less than a handful of proposed gene mutations, but it was in a major journal, the Proceedings of the National Academy of Sciences, good people who did it. And then when Muller publishes his paper in the journal of Science, literally 6 or 7 months later, in July 22 of 1927, Muller, being the kind of guy that he is and the competitor, he never cites the previous person's work. He totally ignores their work, and he won't give them any standing at all.
Wow.
When you write a paper in a scientific journal, you're supposed to have a discussion, and you're supposed to discuss the previous work, how it relates to your work. Maybe their work was wrong, maybe their work was right, maybe he built upon it, maybe who knows what he would have thought, but he owed it to the scientific community to actually discuss those sorts of findings. And the other thing that was crazy about the Mueller experience here, and this is, I mean, this is just bizarre as well. Now, the journal Science is the biggest journal in the world. That in Nature, they're the two gigantic journals. And so if you can get into those journals, you get into their media package, you have impacted the world almost overnight. Now, back in 1927, it was still the biggest journal in the world, and you wanted to get into that journal. And so Mueller knows or thinks he has something big. But Mueller's not a big name scientist at the time either. You know, he's trying to make it as a young scientist at that stage of the game. So what does Mueller do? Well, if you want to take the time and go into find Mueller's paper in 1927 in the Journal of Science, you can find it. It's there. And when you get a copy of that paper, you will see that he presented no data. There is no data in that paper. None. Zero. So when I went there for the first time, I couldn't believe it. I said, here's this person trying to propose the most significant explanation, for biological evolution. You know, he's induced gene mutation. This is going to become the mechanism driver of this process. And Mueller doesn't show any data. I said, now, oh gosh, how is that possible? How did he get into science without any data whatsoever? I mean, nobody gets into science without data. On the most important issue facing the biological community at the time, what kind of a deal did he work out? I mean, what kind of a deal? And so I've often wondered about that. And so I just have to share with the audience that, well, Mueller was a PhD from Columbia, and his advisor was Thomas Hunt Morgan, who was a professor there, big name. And as it turns out, the person who was the editor-in-chief and at that time owner of the Journal of Science was this guy by the name of James McKean Cattell. And Cattell had been a professor of psychology at Columbia and was a very close friend of Thomas Hunt Morgan, Mueller's advisor, and actually arranged to have his daughter become a graduate student with Thomas Hunt Morgan at the very same time that Mueller was a graduate student. And they published some papers together, and they all knew each other quite well. Mueller and his advisor, Thomas Hunt Morgan, published several papers in journals that were owned by and edited by, this guy, James McKean Cattell. And so Mueller knew Cattell, knew the family, actually. And so as it turns out, Mueller, picture this, Mueller knows he's got something that's hot, okay? Mueller doesn't know who's closing in on him, how close they're breathing down his neck, but he wants to be first, because if he's not first, he's the first loser. And so he's got to get there. So he gets in science with no data. And I say, how did he do this? What was the quid pro quo? Was there a quid pro quo? And I have to say that I've been trailing this for a long time. And I bought lots of their letters and everything else, and thousands and thousands and thousands of things. And it's hard to cover everything all by yourself. But about, 10 months ago or so, I'm reading a letter that Mueller writes to this fellow, Meselov Demarek, who is at the Carnegie Institute for Genetics Research in Washington. And as it turns out, he writes to this guy, Demarek, and he says that Cattell has asked him to contact people who attended the 5th International Genetics Congress, which was in September of 1927, where Mueller finally presents his genetics work. And he says that Cattell wants him to contact everybody who has a very interesting paper, invite them to submit them to his journal called The American Naturalist. Mueller would review them all and then make a decision on whether they would be published or not, and Mueller's decision would be final. And so I'm saying, well, snail mail, all this, that's an awful lot of work to identify papers, and there are hundreds of presenters at this, to identify the interesting papers, to write to all these people, to get their papers, to review them all, to then go back and forth as reviewing would do. And and then to make decisions, and then his decision's final. I'm saying that's a full-time job. I mean, who could even do that amongst all your teaching, research, and other things that you're supposed to be doing? I said, but what did Cattell do for him? Cattell actually did what? Got him published in the journal Science with no data, and gave him primacy on the most important topic in the world. And as one would learn later, he was only 3 months ahead of Louis J. Statler, whose picture I showed earlier. This was, in my opinion, the quid pro quo that Muller had worked out with Cattell. Now, it's not 100% certain, but it looks, God, I've never seen anything quite like that one before. And as it turns out, now I say Muller gets his paper, and Muller never submits any data to the Science, so his data could not have been peer reviewed. It was administratively accepted. Just you're reading a paper that somebody is talking about his data, but doesn't show you the data. You can't peer review the data. So Muller avoids going through peer review. He skirts protocol. He avoids it because guess what? If he had gone through peer review, they might have said, you need to do 2 or 3 more experiments. You have to check this more. You have to double check this, because that happens all the time in people's research. And if that happened, Muller might not have come in first. So he avoids that. When he goes to Berlin, that conference that I just talked about, Muller makes a presentation, and then he publishes it in the conference proceedings. Well, I have to tell you that paper that was published in the conference proceedings, I believe, was never peer reviewed. It had no methods and materials. It cited nobody else's work, did not discuss anybody's in relationship to his own work. Even if it was Nobel Prize quality work, the editors of that sort of a publication would have sent it back to him, thrown it in his face, that you have to write this the way a regular science paper has to be written. You have to show how do you reproduce your work. You need very detailed methods and materials. You have to discuss your work in relationship to the publications of others. Everybody does it. That's how the scientists work. And Muller doesn't do that. He gives them a very sloppily written paper. He publishes it in this again non-peer-reviewed conference proceedings. So his 2 major things that drive his issue are not peer-reviewed. So Muller, you might say, well, Muller didn't even know about peer review, but no, that's wrong, because I've tracked Muller's advisor for his whole career. Was he involved with peer-reviewed publications? Yes, he was, from 1893 onward, with the Journal of Experimental Zoology and other journals. No, Muller grew up in a culture, a scientific culture that was very strongly peer-reviewed oriented. You can't use that as an excuse to get away from his responsibility. And so when we take a look at how this started, so Muller makes the big claim. He in his title in his science paper was, he induced the artificial transmutation of the gene. This is a big deal. So see what was happening there is that he said, people could knock holes in chromosomes. The chromosomes could recombine. Maybe there would be genetic changes in the next generation, but that's not what I'm doing. He said, I'm inducing micro mutational changes, and he called them point mutations, little tiny genetic changes, but mutations nonetheless. And he said, that is the driving force behind evolution. And so Muller introduces that concept into his science paper. And so he becomes, he wins over the applause. He's the first one. They don't really quite understand everything that's going on, but it's a major breakthrough. However, his best friend, whose picture I showed earlier, Edgar Altenberg, he goes and he says, Herman, how do you know that you haven't just been blowing big holes in those chromosomes? You're claiming you're inducing tiny point mutations. How do you know that? How do you know that? And so as it turns out, Muller in December of 1927 goes to the AAA Science Conference in Nashville, and he raises Altenberg's question. He knows he's going to get hit by this. He knows he's going to, and he has to answer that question. And then in a National Academy of Sciences paper in 1928, he raises the same question, and he quotes Altenberg saying, Herman, how do you know you haven't produced big holes in these chromosomes? How do you know you have point mutations? And so this is the big battle that takes place. How does he know? And so Muller then gets into some he tries to say, oh God, I'm going to have to prove this mechanism myself. So he has this this plan in which he's going to try to do induce what he calls reverse mutations with the radiation. A reverse mutation is this: you have your red-eyed Drosophila, and you see a mutation, it becomes a white-eyed Drosophila in the next generation. Now, if you then take that white-eyed Drosophila and you hit it with radiation, and it goes back to a red-eyed Drosophila, the next, through multiple generations, Herman says, then you can prove that in fact that the genome wasn't destroyed, but it was just micro changes that it can go back and forth, switching from white to red and red to white. And that's what its mutation is. And I'm just inducing these little tiny mutations. That's what evolution's all about. And so Muller, he calls that a reverse mutation. So Muller, for the next 8 years, he tries to prove this, that he's right by showing that radiation can induce reverse mutations. And so I'll just say fast forward on that sort of a thing. Muller's never able to have convincing evidence that he can do that. Muller's explanation falls flat. And different people got involved with that. They looked at it with plants, they looked at it with Drosophila, they looked at it with a lot of different ways. And every which way they looked at it, Muller's explanation did not happen. Was not credible. At the same time, person who's bringing this forward right in Muller's face is Louis J. Statler. Statler, it's interesting. Statler, publishes his paper in Science a little bit after Muller gets his in, but he's second. But Statler actually shows data, and so he actually played by the rules. But Statler, on a visit to Cornell University, meets up with this lady by the name of Barbara McClintock. And Barbara McClintock, who will later become a Nobel Prize winner, what she does is that she does what they call cytogenetics. She's able to come up with little certain staining techniques that show all the fine features of chromosomes and things of that nature. She's far ahead of the field in terms of what she's doing. But she's working with corn, and that's exactly the plant that Statler's working with, corn. And Statler says, wow, that could be very helpful for me. So he invites her to become a professor at the University of Missouri in Columbia. She accepts and goes there from Cornell. And so he says, take a look at my work that I'm doing with X-rays and corn and so forth. And I'm inducing these gene mutations just like my buddy Herman Muller, but he beat me to the punch a little bit. And so she applies her staining technique to his chromosomes after he's treated them with radiation. And he says, can you give insight into the mutations and so forth? She said, I've looked at all this, and guess what? You aren't inducing point mutations or anything like that. You are knocking big holes in your chromosomes, and they're recombining. You didn't induce gene mutation at all.
Wow.
And so he argued with her, and he debated with her, and they went like 15 rounds between Rocky Balboa and Apollo Creed. And ultimately what happens is that she convinces him that he's wrong, and he adopts her view. It took, it took months, but it actually happened. And so, but then what happened, in addition to his self-doubt, he then says, oh God, if I didn't induce gene mutation, then guess who probably didn't induce gene mutation himself? Herman Muller. And Muller's getting all the acclaim across all the world that he's been inducing gene mutation when Barbara McClintock's findings are suggesting that all he's doing is popping big holes in his chromosomes, and that reflects back on the comments back to Edgar Altenberg. Herman, how do you know you're not inducing gene mutation in your chromosomes? And Barbara McClintock's work comes to the forefront and comes to the fore and actually shows evidence that that's not taking place. Well, in 1931, Statler publishes 2 papers laying that out in the literature. He's a big name. He's a very big name. Muller's a very big name too, right? And so what happens is that this Fifth International Congress, where Muller made his name over in Berlin in 1927, now moves its venue over to Ithaca, New York, to Cornell University for the sixth annual, which is now going to be held in 1932. And so they take three prominent people who are going to give plenary addresses on mutation. And one of them's Rosovsky, the Russian guy that I mentioned, showed his picture. And then they take Statler, and then they take Muller. And so, I mean, you got to picture this situation, right? Muller's the top of his game. They have hundreds and hundreds and hundreds of geneticists there. And see if you have the courage to do this. Statler stands up, draws a line in the sand, and he claims in about 17 different ways that he says this, that Muller confuses an observation with a mechanism. Muller, all he did was he induced, based on Barbara McClintock's data, that he induced large deletions in his chromosomes. The chromosomes re-healed themselves, and this ultimately can result in genetic changes at a visual in the next generation, but it is not a point mutation, and it was not a major discovery. And Statler's of the opinion that both he and Muller made a mistake. They made a mistake. They still had not gotten down to that original question. They still hadn't solved the question of how do you induce gene mutation. Muller didn't do it. And so, but picture you are Muller. You've been living with great applause for the last 5 years. And here's this guy who's a very stable guy, very as big as you are in many ways in the field, who was only 3 months behind you, who believed very strongly the way you did, and now realize that he was wrong in his interpretation, and you are as well. And so these guys, they duped it out in a scientific sense, really from the late 1920s all the way until they died. Really, Statler died in 1954 from Hodgkin's disease. But as it turns out, the data were very non-supporting of Muller's interpretation. And if you go into Muller had a biography written by his last graduate student. It was written in 1981. Muller dies in 1967. And in that, because I often wondered, well, I mean, didn't all this criticism get to Muller? I mean, he had to be human, right? I mean, did he think he was always right? And so the graduate student goes, he's a professor then, but he's writing the book in 81. And he goes, says in the mid to late 1930s, Muller had great self-doubts. And he then had come to the tentative conclusion, well, maybe he hadn't induced gene mutation. And all these things that in fact had been brought forward by Statler. And so it's it was a very pointed situation. And during the course of this, just to show you the emotions tied into this, Muller was himself in late 1931. He was at another conference in which the criticism came forward in December, and then Muller's going through a major, family problem, going through a divorce with his wife. The university is very upset because he's guiding a Soviet-sponsored underground student group at the University of Texas, and he's got pressures from three sides. His scientific standing is dropping off, marriage is falling apart, university is giving him a terrible hard time, and Muller tries to commit suicide in January of 1932, and he with a barbiturate. And as it turns out, then it's great that Muller got the dose wrong, because he gave himself a slightly lower dose than necessary, and he obviously it affected him, but he survived this. And he didn't show up one day at work, and they found him really on the campus and so forth. And he wrote a suicide note, and the suicide note was shared with Edgar Altenberg, and is in the Muller files. But I couldn't get access to it. I tried to, but the family didn't want to share it with me. I mean, I've been quite a critic of Muller, and I'm sure they didn't want me to actually see it. And that's certainly their right to withhold sensitive information. But nonetheless, that's part of the story. But Muller's a smart guy. and he knows he's losing ground, and he's losing ground in multiple fronts. And so, without going into his whole story, Mueller, he knows that if he keeps trying to do this reverse mutation story, he's not going to go anywhere. So he comes up with a new approach, and the new approach is to do what? It's to it's really to take a look at something called dose rate versus total dose. Okay, so Mueller's been having his issues with Statler and others. However, Mueller has strong supporters, and he takes a fellowship and leaves Texas and goes to Germany and links up with this Professor Rosofsky and some major physicists, and working all together, Rosofsky with these physicists, Zimmer and Delbruck, they create really the first ever quantitative, mathematically based LNT single hit model. And they based it upon physics concept called target theory. And it was really to try to account for this linear dose response based upon the gene being the target. And they were trying to figure out exactly how big a gene was, and all these very, very important ideas. But they had a problem because they had their concept wrong, and they were basing it really on data from Mueller, in which Mueller thought that he was dealing with a gene mutation, which in fact it was more that he was knocking big holes in chromosomes, and this model that they developed based upon Mueller's mistake on evolution was that there was no such thing as genetic damage repair. So the model itself was wrong from the start, and this LNT single hit model is the one that was handed down to the US EPA when they went into business in the 1970s. A very significant issue. And as I mentioned before, the evidence mounted that Mueller had induced massive deletions, not gene mutations. He never could counter the challenge that he had confused an observation with a mechanism. So he was losing a lot of ground. And so he decided that he needed to take a different other tack, a different other initiative. And so he was at the University of Edinburgh from 1938 to 1939 over in Scotland. And what he did was he decided to address this with a different question. And he wanted to take a look at how do you assess risk from radiation through total dose or dose rate. And so now a total dose versus dose rate, a total dose is like what I call the piggy bank theory. And that is every single exposure to, let's say, radiation causing mutation causes damage, and that damage just adds up like adding pennies to a piggy bank. And the damage is never repaired. It just keeps getting added to. So you add 100 pennies, you have $1. And so if you keep adding all this level of mutation, it adds up to so much genetic damage. As compared to a dose rate means that there is a capacity of the system to repair the damage. And if you exceed that capacity, then the damage increases. But if you stay below that capacity to repair, then the damage is not seen. And so Mueller said, well, I believe that it's a piggy bank model. And if I can show it's a piggy bank model, then I can extrapolate this all the way down to a point mutation. I can support my gene mutation theory, and I can support the LNT theory, and I can kill two birds with one stone here. And so this is what he tried to do. And he got this student to do a study in which he gave a large dose of radiation, and he took that same dose and he spread it out with another group of flies every day, spread it out over their whole life, so it add up to how much he gave all at one time. And Mueller would have predicted, it did predict, that the amount of damage should actually be the same. And that's the piggy bank theory. And he claimed that there's no such thing as repair. And so guess what happens? Well, as it turns out, the student came back and said the data supports the piggy bank theory. And therefore Mueller's right. And this was a gigantic, oh boy, it just revitalized Mueller. And Mueller was so excited. he got this published in a non-peer-reviewed conference proceedings again.
Mm.
And as it turns out, nobody really challenged this interpretation. Muller runs with it because it revitalizes his career, does two things. But the most important thing ultimately will be for him is that I believe this played a very instrumental role in Muller being awarded the Nobel Prize, because it just revitalized everything and brought back to that and excitement back in 1927. And so when he spoke at the Nobel Prize lecture, Muller highly cited this student's work and how significant it was. And he specifically applied this student's findings to why there should be no support for the threshold model and why you would have to go to an LNT model. It's a very, very significant situation. Now, but the problem was that people, because of Muller's reputation, whatever it was, nobody really examines this person's work. I decide to examine the work. And I get the original dissertation, I get the letters between Muller and the student, of which there are many. I get the comments by the committee, and the audience should understand that Muller was over in Edinburgh and trained the student how to do some important genetic crosses of his fruit flies so that they could become genetically homogeneous. And then Muller leaves and comes back to the United States and leaves the student on his own for the entire period of the research. They communicate only by letters, the letters that I have obtained. And so what I learned from these letters is that the student was not well trained certainly in fruit fly genetics, didn't know how to make the crosses. Muller tried to teach him. The student was frustrated, wasn't doing it well, and complained to Muller that, or apologized to Muller that he didn't think he was quite up to the task at all, that when they piloted the study, they used fruit fly strain A, but then when they tested it, they used fruit fly strain B. I don't know how that ever happened. They had multiple genetic substrains used at the same time, introducing multiple variables within the study. They even changed the fruit fly strain during the course of the study because the fruit fly that they were testing and not had piloted was supposed to have been able to measure two different genetic endpoints at the same time, and it couldn't do it. So they switched over to another fruit fly that hadn't been piloted. There were so many different problems with this research that it never should have even been approved for a dissertation, let alone used and promoted at the Nobel Prize work and revitalizing Muller's career. And I've published all these criticisms now in the literature, but nobody for like 70 years criticized this particular work. And at the same time, something that's particularly important here too, and that is that they used radium to expose the animals to gamma rays. And now when you do that, and they did not state where the control group and the treatment group were they in the same room, were they close together, and so forth. I know in the Manhattan Project, they were in the same room, close together, and the Manhattan Project used a lead shield so it could block the gamma rays from hitting the control group. And the lead shield in the Manhattan Project was 99% effective. And you might think that's good, but it's not really great. In this study in Edinburgh, they never mentioned where the incubators were for the control of the treatment group. They never mentioned if they have lead shielding or not. But I'm assuming they did it like they did in the Manhattan Project because Muller was involved with both. And if they did have lead shielding in Edinburgh, and if it was 99% effective like it was over in the University of Rochester, then the control group would still have received a massive exposure of up to 24 rads of radiation. It would have been unbelievable. And they didn't comment on this in the dissertation and the write-up or nothing. And I somehow uncovered this and then exposed that, well, they can't say anything about this study. Muller's talking about thresholds and LNT and so forth. He can't say anything. It was really a study that had poor scrutiny oversight by Muller. The student the student it was really a pilot study, and they gave much more to it than they ever should have. And this is all like new things that emerged in the last couple of years. Now, and so as it turns out, during World War II, the student in Edinburgh and Muller, they leave right at the beginning of World War II. Muller comes back to this country, and he goes to work in the town that I work in, Amherst, Massachusetts. I'm at the University of Massachusetts. He's at Amherst College, and he gets the job there because the department head was a graduate student under Thomas Hunt Morgan at Columbia in and around the time that he was there. And some of the faculty were being drafted into the war from Amherst College. And so and Muller couldn't get a job any other place. And graduate student gave his old friend a job at Amherst College. While there, the Manhattan Project is started at Rochester, and Muller links up with his colleague, Kurt Stern, whose picture I showed. And Kurt Stern arranges for Muller to become a paid consultant to the Manhattan Project, okay, working on the fruit fly research. While the Manhattan Project is being directed by the Atomic Energy Commission of the United States, and they have two types of research going on at Rochester. One is with a mouse model under the direction of Donald R. Charles, and the other is the fruit fly work with Kurt Stern. As it turns out, you might think that we're going to run with the mouse study because it's a mammalian model, and the fruit fly is not going to be quite as relevant to the human risk assessment as the mice. They used over 400,000 mice in this study up in Rochester, and they started in 1943, and they got no meaningful results during the war and after the war. The only publications I ever got was a 2-page summary in 1950 that was a 2-page summary. And then in 1954, poor Charles, he commits suicide, and the data is lost and the fragments and so forth. And in 1961, some of the old workers came back to try to put together what they could put together. They published a paper, acknowledged there was data missing and so forth and so on. And the field passed them by, and that Manhattan Project with the mammalian model had no impact on anything. Very significant hidden story. And it's a tragic story because of Charles's life and everything. But when you look at it for policy and what it could have affected, we have no relevant information then that we're going to use on mice. So the big focus now becomes on what out of the Manhattan Project? It's the fruit fly research. And that's going to be undertaken by Kurt Stern. And so what happens is that they're going to Muller convinces Stern to replicate this student study that he had just directed over in Edinburgh, because he might have realized that this study had all kinds of weaknesses, and this was his salvation anyways, and he was going to try to replicate it. Maybe they could replicate it. So they got these, Warren Spencer, whose picture I showed you, to do an acute study. So they would give all this big dose all at one time, and then they would get this other person who is going to be Ernst Kasperi to titrate the dose out and give it over the course of a lifetime. So what happens is that in the acute study, what they find is, in fact, that again, they have a linear dose response. They give large doses, and they do about 5 or 6 of them, and they get a linear dose response, and they will ultimately publish this. And people claim that, wow, that supported a linear dose response with an acute exposure. Now, again, nobody criticizes this. 60 years later, 65 years later, I come along, I look at it, and I criticize it very severely. It has very poor temperature control. They've inconsistent instrument calibration. It's very, very weird here. They don't match the control group with the treatment group on experimental days very well at all. And then that's a serious methodological problem. The worst problem, in this study, is that they took fruit flies that were given the same total dose, but with different dose rates, and combined them into one. And that's the hypothesis that they were testing. And they eliminated the capacity to test it. And nobody seems to criticize that. And it was just so incredibly poor. And you might say, well, how could they publish this paper in a journal in which they eliminated the capacity to test the hypothesis that they were trying to test? How is that even possible? And I said, well, it's possible if in fact the person who's in charge of the research is also the editor of the journal that they're submitting it to, because then, you know, it's like the fox is guiding the chickens. And so Kurt Stern was in charge of this research, is the editor-in-chief of the journal Genetics. And he submits this paper to the journal Genetics on November 25th, 1947, and it's published only 1 month later. So you know it wasn't peer-reviewed. It was poorly designed. And again, nobody criticizes this. They use it to support ultimately, you know, their LNT perspective. But the most important thing is they're really in the study by Ernst Caspary, because he took this total dose, this large dose that Spencer was doing, and he titrated it out over the entire life of the fruit fly and wanted to see if it produced the same amount of damage that they saw in this acute study. And what happened was he didn't see any damage induced, none. And he goes in and he shows his findings to Kurt Stern, and he says, Kurt, I'm sorry to tell you, but when we get it in a chronic fashion at a very low dose rate, that was about 1/13,000th of the dose that Spencer gave all at one time. And even with that exposure, I have to tell you, even with that exposure that they were giving, they called it a low dose, right? A low dose. It was still 100,000-fold higher than background. Okay, 100,000-fold higher than what you and I are being exposed to now. They call that a low dose, okay? And they get no treatment effect at that quote unquote low dose, none. And they give that every single day, the entire life of this fruit fly, and they don't see damage. And they do not see damage.
Wow.
And so what happened is that you might think, well, this is a problem. And so, yeah, it is a problem. And so what happens is that Stern says to Caspary, I'm not going to accept your findings. And the reason why I'm not going to accept your findings is that I think your control group was reading a little bit too high, and therefore it biased things, and you ended up seeing a threshold instead of a linear dose response. No, it's too bad. These last 2 years have been wasted, but that's too bad. I'm not going to accept your work. So, but Caspary, he goes into the literature and he digs deeply, and he finds a number of studies using the same model that he's working with, and he looks at control group background genetic variability, and he finds, guess what? His control group was not reading too high. It was reading right where it should have been, right in the middle. And so he goes and he shows these new findings to, in fact, Stern, and bless his soul, Stern backs down. He actually does what a scientist should. He followed the data and he backed down. So this should have been, well, LNT was going to be dead and we're going to support a threshold model. But no, that's not actually what happens here. And what's the new strategy? The strategy is how do we save the LNT? Well, you save the LNT by doing this. Stern gets, I presume, Caspary under pressure to discount his findings. And so what they did was Stern suppressed the significance of the threshold findings by what? By demanding in the discussion of their paper that the data of Caspary not be accepted until it could be determined why the response was not linear, that is, why it disagreed with the Spencer findings. And they published both of these papers in his own journal without an independent peer review. I tell you, I have never seen a study in which the authors said, here are our great new discoveries, and we stand by our findings. We did it as well as we could possibly do it, but don't use our findings. But don't use our findings. I've never seen this ever, but that's what happened in this, and it shocked me. And so I knew at that point that Muller, that Caspary and Stern had seen data that were very significant. And at the same time, I knew for sure, because I had read Muller's Nobel Prize speech. I knew for sure that Muller, in fact, when he went to his Nobel Prize talk, he just praised this study from Edinburgh, and it supported LNT, and the threshold model was dead. So I'm saying to myself, how could Mueller do this? Maybe Mueller hadn't seen the data. Because how could anybody do this if they're Nobel Prize talk and be like almost lying to the public? And so I've got all the correspondence between Mueller and Calabrese and everybody else. And indeed, I found one evening here at this desk, I found that Stern had sent on November 6, 1946, a letter to Mueller, and he gave Mueller the data set and the paper of Calabrese. And that Mueller actually writes back on the 12th of November, 1946, and I got this, I've scanned the whole thing. It's a serious problem. It's a challenge to LNT. I know Calabrese is a good researcher. You have to get more money and test this. This is a serious problem. Now, this was the finest study that had been done. This study, unlike the Spencer study, did not have methodological problems. It was well conducted. But when Mueller goes to his Nobel Prize, what does Mueller say? Mueller only quotes the study from Edinburgh that was flawed to support his case. Did he cite the threshold supportive study of Calabrese? No, he doesn't. He says nothing at all. Nothing. Now, what actually happens is that his lecture receives enormous publicity. It influences regulators, the media, the scientific community on public health concerns with ionizing radiation, even at low doses. And the big lie is born. Okay, the big lie is born. It's got the big thrust here. And so we know now that prior to his lecture, Mueller knew of the threshold supportive study of Calabrese based on the letters. It was the strongest study to date. Mueller knew that it challenged LNT and he strongly supported replication. In fact, Mueller found no technical issues in this, no problems with Calabrese paper. Letter exchanges indicate that Mueller's views were similar 5 weeks before and 5 weeks after his Nobel Prize lecture. I have a letter dated January 14th, a detailed letter, 1947, in which again, Mueller finds no technical issues with the Calabrese study. It's very, very interesting. So following this internal review by Mueller and Calabrese, the threshold, this is of the Calabrese paper, the threshold conclusion was dropped and Mueller's name was added to the acknowledgements. So what happened though after that is that yes, indeed, they tried to replicate this study. And it was replicated by this lady called Delta Uphoff, as directed by Kurt Stern. And this study, Delta is trying to do the Spencer and the Calabrese study replication herself. And in her first experiment, which was really looking at an acute study, her control group was about 40% below that in the field and below that of Calabrese. And because it was so low, when they wrote their report to the funding group, which was the Atomic Energy Commission, they said their data was what? It was uninterpretable. Uninterpretable. Now, and then at the same time, what they did was Stern blamed the low controls of this Uphoff replication. Guess what? They blamed it on investigator bias, suggested investigator bias. I mean, this was actually pretty unbelievable. They thought there may be they weren't sure what was causing it. But whatever it was, they then went on and did two more experiments. One of the two experiments had another very low control group that they couldn't interpret. The third experiment had so much damage that the damage was like 3 to 4 times more than what an LNT would have predicted. When he looks at all three studies, he must have said, God, what has happened? None of these studies are interpretable. We have a problem. Charles isn't doing anything, but what he does is he pulls a rabbit out of a hat. And that is that this is Stern, he basically discounts the Calabrese study, which was the only good study that he had. And then he doesn't share with the scientific community that he had found that 6 months before he had found the Delta Uphoff research uninterpretable, and there was possibility of investigator bias. And he combines these all into his version of a meta-analysis, and he publishes it in Science and says that the research at his Manhattan-funded project at Rochester supported a linear dose-response relationship. And he publishes this in a 1-page, 1.25-page paper made up of one big table of these different experiments, showing no methods and materials, no statistics, none of what you have in a paper, and then promises, in Delta promised to provide all this in a subsequent paper, which they never publish, And the papers that are cited to support LNT by the forthcoming National Academy Committee are the Spencer paper, which was flawed, and the Delta Uphoff research, which is not only flawed, it's the findings with the chronic studies, we don't know where the data are. And then recent evaluations of the study design show that the Delta study design incorporated 2 different variables studied at the same time, which meant that you couldn't even draw a conclusion. It was a wash for the Manhattan Project, yet these studies provided the basis for LNT. And so the Calabrese studies became marginalized. People claimed that it had a high control group, which was wrong. And the weird thing here too, that the audience should know, is that Stern actually went to Muller, wrote him, and I have all these letters, and says, can you tell me which control group is right? Delta's control, or Muller's group? You've been working with all these control groups because you're in your fights with Statler. Which control group do you support? And Muller, and I have it, Muller writes back and said, my data matches with Calabrese, not with Delta's. Now, I've got this in letters and cables and everything else, okay? And that's what the data actually report when it's published.
Mm-hmm.
Now, but the interesting thing is that in 1950, what happens is that's what these letters are found in the cables and the like, yeah. But in the early 1950s, Muller, this is so weird. Muller, who's got a Nobel Prize then, right? He repeatedly and inexplicably challenges the Calabrese findings in writing, and he claims that Calabrese control group values were aberrantly high. Yet the data of Muller, both before and after the Calabrese paper, and all those letters between him and Stern over the matter, contradict what he says. Now, so I know that Muller was lying in those papers because that's where the data were. And so what would make Muller in these 4 or 5 papers in the early 1950s knowingly make false comments? And so this is this incredible story, this Nobel Prize guy. The only ones who knew he was lying would have been Stern and Delta and Calabrese, maybe Spencer, I don't know, maybe some others, but a very, very close group. But there was a paper written by this very famous MIT health physicist by the name of Robley Evans in Science, who supported the Calabrese perspective and who was communicating broadly with all these other geneticists across the globe. And Muller got wind of this and wrote to Stern to try to stop it, wrote to Evans himself. And I think he was losing control of it. So I believe that he had to come in and drop the hammer and stop Evans from doing this. And he writes these 4 different papers. And so as it turns out now, we know the 2 key Uphoff control experiments, the data have never been published. The data have been missing for over 70 years, yet it's the basis of LNT in this country and the world. No information exists on the 2 chronic studies of the Uphoff beyond this 1-page summary that I mentioned. Based on study design information that I have studied, it's been recently shown that these studies had 2 simultaneous variables. It could not test the total dose rate hypothesis. Studies so fundamentally flawed, even if the data were found, it's just fundamentally flawed. And so Stern publishes a couple of highly acclaimed genetics textbooks from 1950 on. In it, he claims that the data of Uphoff and Spencer, which are totally flawed, provided the basis for the linearity interpretation, ignoring Calabrese finding, and the big lie continues. But in 1956, what happens is that the Rockefeller Foundation creates a a genetics panel. And they do this genetics panel from the National Academy of Sciences. Now, Rockefeller Foundation, they wrote to President Eisenhower and they said, we have a big problem with all things nuclear. We need to get control of it. We need a National Academy of Sciences committee to oversee and advise the country. And that's probably a very good idea. And so, as it turns out, one thing that maybe people don't know is that the president of the Rockefeller Institute for Medical Research, which becomes Rockefeller University soon thereafter, that person who's the president of that is also just happens to be the president of the National Academy of Sciences, the same person, holding two different jobs, a Rockefeller job and a National Academy job. And he's at the same time, a third hat, he's on the board of directors of the Rockefeller Foundation, same as Detlef Bronk. So the Rockefeller Group is controlling what? It's controlling everything. It's making it happen at the level of the president. It's got its person involved in being president of the National Academy of Sciences. And then they put this committee together. It's going to be 6 different panels, but there's a genetics panel that's going to be created. Now, you have to understand, if you're listening to this, in the United States, up until that point, there's been different advisory groups in medical questions that have advised the country. They've always had a medical advisory group, and on that medical advisory group are always a couple of geneticists along with other medical disciplines. Now, when it came to dose response issues and safety and so forth, the general medical community favored a threshold. The geneticists, because of Muller, always favored an LNT. They were always outvoted, always outvoted. The predominant view was it was a threshold. Now, what happens in 1956 is an absolute game changer. You talk about how a subtle thing changes everything. It's like changing the rules. It's like making the basketball hoop instead of 10 feet, 20 feet tall. It's making it maybe 3 feet tall. It's changing the rules. So what they do is that in addition to having a medical panel, for the very first time, this National Academy of Sciences will have a genetics panel. Now, you might say that's a good idea. Well, what actually happens here is that Warren Weaver, who is not a geneticist, is put in charge of the genetics panel by Detlef Bronk. Warren Weaver, as we mentioned before, is the director of research for the last 30 years for the Rockefeller Foundation. He has provided the major funding for all the academic geneticists in the country because the US government was not involved with funding that research as it does today. And Weaver knew everybody's MO, knew their views, their written views, their unwritten views, as happens when you fund somebody for multiple years and so forth, as they did. And he selected the geneticist that would be on this panel. And he selected only those who had a clear, strong belief in what? The LNT. So it's like choosing a jury, and you know what the jury's beliefs are before you have the trial. It's a stacked deck. And so, and the interesting thing is that so when I knew how it was all going to come out because I knew the answer when they went LNT, but I wanted to go in and I got the copy of the transcripts of their meetings, and I wanted to see, well, how did they debate? Who supported threshold? Who supported LNT? What were the persuasive arguments? I can tell you for sure that there was no debate on this issue, and that one of the members, Tracy Sonneborn, who was at the University of Indiana, colleague of Muller there, he wrote the equivalent of the radiation geneticist Apostles' Creed, and he read it into their record, and that what they believe in, and they believe in all damage is harmful, it's cumulative, it's irreparable, it's irreversible, and it translates into a linear dose response, period, no debate. They all affirmed that was their belief. Now, this was so strikingly important and so missed within the framework that they could have quit right there because the decision was made. They actually had 7 or 8 other meetings planned because that's how bureaucracies work. They were going to force them to do make work, and they did, and that make work becomes very significant here as well. But I want to share with the audience one thing else, and that is this is 1955 November when they first meet. Now that's 10 years after the dropping of the bombs over in Japan. Now James Neal, whose picture I showed you earlier, he spent 10 years directing this atomic bomb casualty study, looking at mutations in birth defects and so forth, in the offspring of people who were exposed to the atomic radiation from the explosions. He studied 75,000 offspring over 10 years. Now, most people who aren't geneticists, and maybe people who are geneticists, I don't know how their thinking is on this, but you would have thought that being the offspring from parents who were exposed to the atomic bomb would have resulted in significant increases in a whole series of birth defects and other irregularities, which should be documented in well-defined studies. And these were his best studies you could possibly do. And guess what? Neal's group, his research team that was doing this National Academy of Sciences study, found no increase, no treatment-related increase in adverse genetic effects, none. And so he has a 10-year summary study, 350-page or so report that he sends to Muller and he sends to Detlef Frank and so forth, because he wants this to be reviewed by the panel. That's what they're supposed to be doing. And at the very first meeting, what actually happens is what? The panel, under Muller's direction, said that the negative findings after 10 years are illusionary, and we should not at all evaluate this. And so Muller, because he's the strong man in the room, Muller basically forces this panel to follow his lead. And this study, that a 10-year study by two countries, Japan and the United States, under the direction of the National Academy of Sciences, under the direction of James Neal, Michigan professor, and a member of that committee, is not going to be looked at.
Wow.
And is not looked at and is not shared with the media later on, hidden. Neal, I got to give him credit. He gives that study over to a parallel group in the UK, and they use his study and find it valuable.
Let me ask, at the point of this, the rejection of consideration of this study, you've talked about the sort of personalities involved and people's personal aspirations and so on. Do you have a sense that there's something else going on here outside political pressure, in terms of a desire outside the scientific community for the panels to come up with certain conclusions, or what else might be at play here?
Well, I think there's actually a bunch of things that could be in play. There's certainly ideology, and there's self-interest that's operating here as well. For example, Muller was a lab-based scientist. Okay, he's a lab-based scientist. Neal's work is population-based. There becomes a fight between lab-based people and population-based people over funding money, because they think that the amount of money is going to be a fixed amount of money. So if the money is going to be shifted to human population studies, then guess where it's going to be taken from? It's going to be taken from the lab side of it. Or if it goes all in the lab, then if you won't do the human population studies. This was their mindset. And I have to share with the audience here, and that is that just picture yourself, you are Neal. You have worked 10 years on this study, and it's not just you. You have dozens of other people working on this study that you are directing. These are talented people, and then their work. Just if you did a dissertation, you spend 3 years on your dissertation, 4 years on your dissertation, and then you come to the committee and they say, I'm not going to read it. Well, this guy, he's already a PhD and an MD. He's worked on 10 years on this study. He has a staff. He's doing it within the framework of the National Academy of Sciences. And this committee says, no, we're not going to look at it. And so I can only imagine, if it were me, I would have just gone totally ballistic and outraged, and I'd have had a big fight with these people. He did not fight. He did not fight. And you'd have said, "Oh, what the heck is the matter with Neal?" But I can tell you, that was in November of 1955. Their report comes out in June of 1956. in August of 1956, Neil is over in Copenhagen at a big conference and a follow-up meeting with the World Health Organization. Muller's there as well, and he decides to take the gloves off, and he decides to challenge Muller for the first time publicly and say, listen, we need to base these evaluations on human data, not on fruit fly data. And the New York Times wrote about this because there was a big brouhaha at the conference, and they said there was a big fight between the Mullerians, which are the followers of Muller, and the anti-Mullerians, which were the followers of Neil. And they ultimately, this big fight spread over into a World Health Organization meeting in Copenhagen the very next week. So they had 14 days together, amazing. And Muller tried to prevent the publication of Neil's findings in the World Health Organization report, and a bunch of British geneticists who he had shared his report with threatened to walk out of the meeting if Muller prevailed. And ultimately, what happened is that Muller did not prevail. There's lots of conflict that took place, but in those letters at that time, there was a lot of fighting over research money, research dollars, who was going to get it and who weren't going to get it. And it was breaking down to Muller trying to protect, his research dollars. I mean, that's one of the aspects that are going on. It's more complicated, obviously, than that, but there's multiple self-interest components going on here with that. And the interesting thing over here is that if you think that's bad, it gets worse, because, and how could it possibly get worse? Well, as it turns out, this committee, because they right off the bat, they decided that what do they believe in? They believe in LNT. That's it. And so Warren Weaver had to give them make work, because they still had to meet 4 or 5 more times, because they had the budget to meet 4 or 5 more times. And so he gives them an assignment in February 5th or 6th of 1956. And he wants them to estimate the number of genetic birth defects and so forth that happen in the US population if they were exposed to a certain level of radiation one time or over 10 generations, and a few other permutations like this. Well, but they had to assume that there was a linear dose response. But I want you to figure out give us the quantitative numbers of adverse effects if you have 160 million offspring, because that's what the size of the population was in 56 in the United States at the time, what they were going to expect. And so as it turns out, gave them 1 month to come up with their estimates. There are 12 geneticists on this panel. 3 say that's a crazy thing. Nobody could do this. We're not going to do it. 9 of them decide to do it. And I have all 9 reports. Now, these reports come in and they're sent to Jim Crow, whose picture I showed you earlier. Crow looks at these and he kind of freaks out, because these estimates, even though they should have been very similar, because they're all forced to assume an LNT relationship, they were all over the lot. They didn't agree with each other at all. They had all kinds of inherent uncertainties within each individual, and then they all disagreed with each other. They disagreed by thousands and thousands of fold. And so Crow writes to Warren Weaver and says, this is a terrible assignment. When we look at this, these people, they don't agree with each other at all. If we come up with recommendations, nobody's going to believe it, because they'll look at how much we just don't agree with each other. We couldn't agree with each other, so we're going to recommend something to the country. This is a problem. And so what do you do when you have that problem? Well, you could throw it back to the committee and say, let's figure this out. But that's not what actually happened. What happens is that Jim Crow on his own, you can believe this, Jim Crow on his own removes the 3 most divergent estimates. So he takes it now from 9 to 6, and he reduces the uncertainty from many thousands of fold down to 750 fold, with just to reduce the uncertainty, right? And then 750 fold is still too much. So then they make a de facto non-scientific nothing. They just say the variability is 100-fold. And they came to the conclusion that that's probably what people would accept as normal amount of argument, debate, and uncertainty. We can live with that. But they felt they would have no credibility if they were honest and so forth. So when they published that report, they published it in Science, and they also published a separate report to the public. And they say in both of those that only 6 people of the 12 took up the challenge. And I know for sure, because I have them in behind me, in my file cabinets, that there were 9, all 9. And so this committee, this National Academy of Sciences committee, altered the research record and created and committed scientific misconduct in their publications in Science and in their National Academy of Sciences publication, which was a popular publication that was sent to every library in the country. And so and to make it all worse in this story, the popular report was alleged to be written and approved and so forth by the committee, was actually written by a third party. And this Bear One committee never read the public report, never approved it. and they found significant errors in it, and they never acted to correct the errors. And why wouldn't they act to correct the errors in this public report? Why? Because they're getting funding from the Rockefeller Foundation. And who is the chair of their committee but the director of research funding for the Rockefeller Foundation? Who's the chair? Who's the president of the National Academy of Sciences but the president of the Rockefeller Institute for Medical Research, who's also on the funding board of the Rockefeller Foundation? So all these panel members that saw the public report that is alleged to them that they never read, approved, it's all full of major errors. They say nothing. They say nothing. So you have a failure of ethics. And I can tell you, when you create science, when you cause scientific misconduct by misrepresenting of the research record and doing it so deliberately like they did, you lose your jobs. You don't get awards named after you. You don't get big prizes, but they did.
Or you shouldn't. Yeah.
Yeah, all of them did. And so this becomes this report becomes very significant in a lot of ways, because what happens is that the Atomic Energy Commission was really favoring more of a threshold sort of an approach. They felt that this committee was overexpressing the damage and great concerns. They were trying to deal with the fallout issue at the time. And what happened is that by going so public and making this so scary, so to speak, to the general public, because no level of exposure was safe. There'll be all kinds of new birth defects. There'll be all kinds of new cancers. There was this sort of a thing. That what actually happened is that in the political process, Eisenhower and Congress lost credibility, lost faith in the capacity of the Atomic Energy Commission to guide the country when it came to cancer risk assessment or radiation risk assessment. And at the last year of Eisenhower's presidency in 1959, Eisenhower created the Federal Radiation Council that actually took over the risk assessment activities on radiation from the AEC. And it was all because of this particular fomenting that was coming out of the Mueller-led Bear One committee. Now, at the same time, you might think that, could it get worse? Could this story get actually worse? And actually, it gets worse. It just gets, this is like our history. But it really needs to be understood. In 1956, one of the members on this committee, his name William Russell, whose picture I showed you, along with his wife, Leanne Russell. Now, they started a major longevity and cancer study in 1956 with mice, and it ends towards the end of 1959. Now, this study gave a very large dose of X-rays to mice, and they were studying the offspring of the ones that were exposed, and they were expecting significant decrease in longevity, significant increase in cancers, very large study, very excellent study. And so what happened is that they saw no impact on longevity. They saw no impact on cancers. And said, oh my goodness, how is that possible? what did everybody think about these new findings? It's coming right out of this national laboratory at Oak Ridge by the best people in the world on this. Well, it would have been nice if it was shared with the scientific community, but William Russell decided to what? To hide the information so that nobody would know about it. So he didn't share it with, he didn't publish it. He didn't share it with the Bear Committee that he was on. And he was an advisor to the Federal Radiation Council, and it hid it from them as well. And this was at a very crucial time. Now you might say, well, how did I discover this? Well, as it turns out,
How did you?
well, how I discovered it was that in I was talking with a person who worked with Russell for many, many years. His name is Paul Selby. This is about a year or two ago. And Paul Selby tells me, he says, well, he said, I published a study in 1993 in the journal Mutation Research on X-ray induced cancer in mice. And that study was undertaken when I was 7 or 8 years old. And I'm saying, well, wait a minute, Paul, you got your name on a publication of a study that was done when you were 7 or 8 years old and couldn't even spell the word genetics. Is that right? He said, that's exactly right. I said, I have to know the story behind the story. He said, well, the story behind the story is this, and that is that this study was done, as I've just summarized, and then it was all forgotten and hidden. And then in 1991 or two, there was a big lawsuit in the UK concerning atomic, plant workers and the effects of exposure to radiation and how it affected their offspring. So it's kind of very parallel to this, what this study was about. And what happened is that a person from the United States, whose name was Arthur Upton, was hired to be a consultant, expert testimony person to the defense at the UK trial. Now, Arthur Upton was a big time person. He was a head of pathology at Oak Ridge during which this study was done. So he knew about the study, but he later went on to become, guess what? The director of the National Cancer Institute for the US, the top person in the country. And then he also became the director of the National Academy of Sciences Beer 5 panel that had their report in 1990. And as I looked at it, Upton knew of this negative cancer study, and he never once let the cat out of the bag. He kept it quiet, just like Russell did. But when he was hired to be a consultant for the defense, guess what he does? He calls up his old friend, Bill Russell, and says, Bill, that study that we have suppressed for 35 years, I need it now to win this case in the UK. And so what happens is that, will you cooperate? And Russell says he'll cooperate. And so then the lawyers and consultants fly out to the US, and they all go down to Oak Ridge, and they all convene, and they develop a plan to get these data that were suppressed for 35 years. Now they have to be published so that the defense can win. And so what happens is that they have to get this paper published in a good journal, and they have to get it submitted before Upton gives his testimony. And so if you can believe this is what happened. On the very first day of Upton's testifying in the UK on this is the actual day that this paper is submitted to the journal Mutation Research in this country. It gets accepted, and the paper plays a significant role in the ultimate decision whereby the defense wins the case over in the UK. Now that's 1993. Now I learned about this through conversation about 2 years ago. And so this is all, nobody knows about this. So then I'm talking to Selby. And so he and I then write a paper that's published about a year ago, in which we write this big cancer cover-up between William Russell and Art Upton. And then I try to reflect upon, well, how would this have changed the course of risk assessment if, in fact, this had been published in 1960, 61 in that time period by a very prominent lab, a very prominent person who's on all these major committees. And it shows that, yeah, because the argument at the time was, oh, this is shortening lifespan at these doses. It's shortening, it's increasing cancer risk. These are massive doses. These are massive doses, and they're having none of these effects, right?
Hmm.
So at low doses, they'd be having even, doses that you can't measure at high doses. I mean, you're expecting to measure these at low doses. I mean, this is, and this was hidden. However, the disposition should have been, that data needed to be out, but it was not shared, and it showed more duplicity and ethical violations by our leaders.
And at the time, so I know we're on part of a century-long history, and partly I want to get through it to then come back on some details. But at this point in the history, what are some of the effects that the bad rulemaking on the basis of this incorrect model are having? Is this affecting nuclear plants? Is this affecting industry? What's going on at the time with this?
Well, the first nuclear plants go online in 61. Okay. And it's interesting because the nuclear plants are going to be emitting some sort of low level of radiation into the environment. And they base their entire emission standards on the recommendations of that 1956 panel that Mueller's on. This is so interesting, right? They base it upon that. And it's really based upon trying to reduce genetic damage. Okay, that's really what it was based upon. However, now, then I have to kind of, and we have a series of nuclear plants that are, this is like the 60s. They were really trying to build nuclear plants and get them going in this country. And so then what happens in, a big controversy happens starting in 1969. There is a laboratory. It's part of at that point Department of Energy now. It's out in Lawrence Livermore Laboratory out in California. It's part of the whole DOE complex, but it's a big one. And so what happened is that they have a concern, and they have a person whose name is John Goffman, who is as a physician, but he's also a PhD in nuclear chemistry. He's in charge of their radiation health evaluation. And so what happens is that there's another person who's a professor of physics at the University of Pittsburgh, whose name is Sternglass. I think Ernest Sternglass. And Sternglass, around 1969, publishes a whole series of papers, but in popular magazines, gets on all kinds of television shows and the like. And he's claiming that fallout and other exposures to radiation and so forth have in fact had a massive impact on the unborn, has resulted in hundreds of thousands of fetal deaths and so forth, many different sorts of cancers and the like. And he gets on all the big television shows and all the big radio shows, and he's every place. So he was so people came to people in the Atomic Energy Commission. Then they came to Goffman, and they said, you have to try to criticize this guy's work. So one of the staff people, a person by the name of Arthur Tamplin, is essentially told to do this. And so Tamplin criticizes and finds all kinds of flaws in Sternglass's logic and science and so forth. But he doesn't really dismiss the fact that low dose radiation could be responsible not for hundreds of thousands of deaths per year, but maybe 4,000 to 8,000 deaths per year. And so he shares that with Goffman and with the leadership of the AEC, and this created a conflict with the upper management, because the upper management really did not want to have this broadly discussed, and they tried to modify the presentation. They try to somehow, you might say, submerse it, so it wouldn't put too much pressure on on their regulations or the growth of nuclear power or things of that nature. And so Goffman and Tamplin, they fought against this administrative control, and it became almost overnight very explosive and very argumentative and very insulting. The language was actually pretty incredible between these groups within the AEC. And this led to congressional hearings that were chaired by Senator from Maine, Edmund Muskie, and other people were involved in this. And Goffman and Tamplin did not back down. And the AEC decided that they were going to undercut the credibility of Goffman and Tamplin by bringing in their other funded scientists who could criticize Goffman and Tamplin. And it became a major fight in front of a Senate committee. But Goffman and Tamplin, I mean, these guys were fighters. They went on 5 days in a row on national, morning television, like I think it was a CBS, morning show, and they are taking on their administration. This became a very visible situation, and what they're claiming is that the emissions that are coming from nuclear power plants, if it continues to grow and throughout the country, that it would be responsible for about 10% of the cancers that occur in the United States population. Very, very large number.
Wow.
From that technology. And so and the AEC administration thinks that they're totally wrong. And so there's this, and so what happened with that is that, and this becomes very significant in the big picture. It's out of control. It's out of control. The media's got a hold of it. Everybody is getting really upset, and Ralph Nader's getting involved. There's a lot of activism involved, things of that nature. So the Congress decides, what's the solution to this? We have to have another National Academy of Sciences committee. So in 1970, because of Goffman, what happened is that they create a new National Academy of Sciences committee called the BEER Committee, the Biological Effects of Ionizing Radiation Committee. And it gets created in 1970, and it makes a recommendation in 1972. Now, Richard Nixon is president, and what Nixon does is that he reorganizes the environment in 1970, and he takes the Federal Radiation Council that has been guiding the country, so to speak, in the aftermath of this bear one, and he eliminates them and puts them into this new organization called EPA. And so he takes this now very, you might say, LNT leaning FRC, very strongly oriented LNT, and he sticks them structurally within EPA, and they become the driving force for LNT radiation advocacy that continues to the present day. That's like a major structural change.
Huh.
So what actually happens then is that this committee that was put together, the BEAR Committee, the person in charge of the genetics panel is none other than Jim Crow, the one who eliminated the 3 most variable, estimates in 1956. He's now guiding it in 1970 to 72. And then you also have William Russell on that committee. And William Russell is the one who has suppressed the data. And Russell still is suppressing the data and not even telling the members on that committee that he's on that BEER 1 committee from 1970 to 1972. So you have ethically compromised people leading this country and making, and this will be the committee that will make the recommendation to EPA to do what? To go linear. And as it turns out, William Russell is a complicated man, because in 1956, Russell actually discredits one of the piggy bank theory of Muller. He's working with mice, and he's, for reasons that are complicated, but the bottom line is that when he took a high dose of radiation and he titrated it into lower doses, he found that the spermatogonia in male mice and the oocytes in female mice, when you exposed them in this fashion to high dose and low dose rates, that at low dose rates, there was such a thing as DNA repair taking place in the male and the female. And he shows that unequivocally, and he publishes it and gets a major paper published in mid-December of 1958 in the Journal of Science. Very, very big discovery. And so what happens is that he finds that for the female, for sure, that there is a threshold dose response. Now, for the male, shows a very strong capacity to repair damaged DNA, but it doesn't, in his studies, show that a threshold yet. But the female had, and so this becomes an important point. Now, what happens is that now it is fast forward from 58 up to 1970 to 72, and Russell's on this committee. He's suppressing his earlier study that didn't show the cancer and didn't show the longevity effects, but he's also got this DNA repair study that is showing a threshold for the female, and it's a large study. He has used over 5 million mice in this study. This is a massive study. This is the strongest study in the world. And so they have a debate in this group. Should they go with linear? Should they go with threshold? The female is showing a threshold, the male not yet. And so the committee, in their wisdom, they decide that they're going to base LNT on the Russell findings, and they're going to base it on the male that does not show a threshold yet. And they make that recommendation in 1972 to the newly formed US EPA. And then the US EPA, in writing, acknowledges that they will adopt LNT, and they'll be basing it upon the findings of William Russell. This is very important to know, because this then motivates the EPA and well, soon thereafter, because EPA is going to have to deal with not just radiation, but they have to deal with chemicals. And so they need a cancer risk assessment policy that applies to both. And in the writing up of the cancer assessment group of EPA, it was LNT was applied to chemical carcinogens because they also induce gene mutations, just like radiation. And then they will also have this LNT applied to them. And so it all got merged into one. And I'll fast forward this to bring this up to date. So what actually happens now is that you think, well, it's all said and done, that's it. But this fellow, Paul Selby, that I mentioned to you before, right? Paul Selby has worked at Oak Ridge since 1966 as a graduate student. It's now 1994. And the Russells are getting, Bill is already retired. Leon's getting ready to retire. And the administrators of the Department of Energy say, you have to save all your data. We got millions of these mice, and you have to computerize it all. They didn't know how to do that, but Paul Selby did. And so they asked Paul to do that momentous work for them, go into the files. He was their person for 30 years anyways, right? And so Paul goes into their files, and it's going to organize all their data. And in the course of doing this, he finds a study in their control group in which they have a whole series of what he calls cluster gene mutations that the Russells never included in their control group data. He finds that certain mutations occurred and then were put aside and not used. And then he remembers the same thing happened in some other experience with William Russell, and that data was ignored. And then there were some other technical features to it. And this was very troubling to Selby, he shared with me. And so what Selby did was that he felt that this could undercut the entire credibility of the entire Russell program. So he then reports this with documentation. He reports these anomalies to the administration of the Department of Energy. They thought that this was significant. They told him to go and sneak back into the lab and find more anomalies. He goes in and this is interesting, he goes right back to it's the very first study that the Russells have. They have a folder called cluster mutations. He opens it up, and in the very first the very first study, they had 90 mutations in the control group that they chose not to include, hidden. And if they had included it, it would have showed the control group mutation rate would have been profoundly higher than what they used, and it would have markedly decreased the risk of radiation. Then he looked and he found more and more and other examples of this, and he made it available. And the next thing you knew, they shut it all down, and they had a major hearing with 4 outside experts who came in 1995, with Selby now challenging his former mentors and bosses, William Russell and Leanne Russell, that they may have created scientific misconduct. They had scientific errors, he argued, and who's right? So this panel looks at all this, all the transcripts, and I have all that information. The bottom line is that the panel did not want to get into, saying that they did not want to register their opinions on whether there was scientific misconduct or not. They didn't make a ruling on that, but they made a ruling that the Russells made a mistake, and that they made a ruling that Selby was right, that they had mutations. The mutations needed to be counted, needed to be incorporated into the risk assessment process, and they told the Russells and they told Selby to correct the scientific record. So the Russells attempted to correct the scientific record, and they published their findings in the national and in the proceedings of the National Academy of Sciences. And as a result, and then Selby did the same in a couple of the genetics journal. The bottom line is that the Russells made a mistake in their control group. Now, you might find this hard to believe. These are the best people in the world, right? Most knowledgeable people in the world. They made a mistake in their control group by 160%. They were lowballing the control group by 160%. Now, what that does is it magnifies the cancer risk and mutation risk by a profound amount. And if you make the adjustments, if you could actually make the adjustments now by correcting the control group error, what that did was it made the dose response for the radiation in the Russell study for the females not just a threshold, it made it hormetic. It was beneficial.
Wow.
And then for the male that was before it was a linear dose response, it now made it a threshold.
And you think that they just directly cooked the books here with this error?
Well, my view is that they were young back in 1951 when it all started. They were trying to create their career. There was a major effort major financial investment into what they were doing. If in fact they had exposed or shared honestly with their administration and the scientific community that in fact they had these irregularities which took place, that the risks, if they included them, of the radiation would have been somewhat trivial. The investment in their careers and the investment in the program at Oak Ridge would have been minuscule compared to what it was. There was massive self-interest there. And the interesting thing is that they kept getting these gene cluster events throughout their whole career, and they kept this, for the most part, totally hidden. It was only because Selby inadvertently came upon it and had the courage to pursue it, actually, in many ways, a heroic event that took place. And so what happens is that this gets published in 1950, 1996, 1997, 1998 time period. Nothing actually, Selby loses his job with them because he challenged them. And this is also interesting too. And so he's just trying to survive. The Russells are old and, getting ready for retirement and so forth. They're trying to preserve their situation. 20 years goes by. I somehow become aware of this. I then do a deep dive into it and I unplug it. And then I apply it back to, well, what would have happened in 1972 if the mistake had not been made?
Well, let's take that up after just a short break.
Okie doke.
Okay.
What I'd like to do is to now take a look at the key LNT findings and put them in perspective. What we've learned is that Muller's evolution concept of a highly stable genome and no genetic damage repair is now proven incorrect. Muller's gene mutation claim is now proven incorrect. The LNT single hit model is based on Muller's incorrect interpretations. Muller was deliberately deceptive in his Nobel Prize lecture. Muller and Stern misrepresented the Manhattan Project findings to promote LNT. The Bear-1 genetics panel, 1956, it misrepresented the scientific record to promote the acceptance of LNT, and in their Republic report was not written or approved by them and contained serious errors. The beer genetics subpanel of 1972, well, it was a massive project, involved actually more than 5 million mice. It provided the new basis for LNT because it was based on mice, gave that information to the EPA, and yet a major error was discovered by Paul Selby 2 decades later. And then when this was corrected, it indicates a threshold or hormetic response should have been established. So why did LNT succeed? Well, because producing mutations was a major advance. Evolution and mutation concepts, they really overwhelmed the field and became integrated within the LNT model. The key studies were not peer-reviewed. The Edinburgh study, which is the Ray Chahori study, had this whole series of flaws that I mentioned to you. The Uphoff studies have never been published. The data are missing, and they have been, their design was actually a flawed study design. But yet the Manhattan Project, coming under the influence of the Atomic Energy Commission, had massive influence. Dropping the A-bomb frightened the world. The Nobel Prize created the platform for Muller's ideology. It's really a perfect storm. The Cold War, with the above-ground testing of the atomic bombs, created even more fear. And then step in the Rockefeller Foundation. They created what? A separate genetics panel, and they stacked the members so that those people would be promoting an LNT ideology. Nobody sees this happening. The National Academy, with this committee that lies and has deception, but it's the National Academy, and it has a great appeal to authority. You know, all these things merging together. Then in 1959, 1960, you have Russell does this cover-up. And then with all the attendant mistakes and dishonesties that have come forward. Well, what we've found here is that the scientific, radiation, and toxicology communities, guess what? They got the LNT question wrong. Self-interest and scientific misconduct also contributed to leading to the LNT. All the errors, the deceptions, and the mistake, guess what? They were given a pass, and they still are given a pass by the scientific community and by the media. The scientific, toxicology, and regulatory communities failed in their oversight, review, and leadership. Now let's take a look at the journal Science. Science is like the National Academy of Sciences. It's like we look to that for leadership. Yet Science published 4 key papers that were deceptive. 1927 Muller, a paper without data and peer review. The Uphoff and Stern paper in 1949, guess what? No methods, no analysis, and with a fundamentally flawed design. The Bear-1 genetics panel publishes a paper in Science recommending to go linear, and guess what? It's made up of what? It's made up of misrepresentation of the scientific record. They committed scientific misconduct, and at the time, one of the Bear-1 genetics panel members is one of the 6 senior editors at Science. I mean, it's a sorted sort of a mess. And then you have in 1957, we have the story of Edward Lewis, where he promotes a linear dose response relationship for radiation risk assessment. And in Lewis's story here, within a week or so of him having his paper published in Science, he gets his paper gets debated on Meet the Press. He gets to testify in front of Congress. He gets big picture full story in Life magazine. And when one goes and looks back into his paper, one finds that, in fact, what happens is that He improperly uses other people's data that said that it should not be used for low dose radiation risk assessment and uses it, never identifies these limitations. He brings terrible bias to the evaluation, and ultimately it becomes a very significant paper. The Science Journal has a very major role in the acceptance of the incorrect and fraudulent history of LNT. So, final slide for final time here. The entire regulatory programs and public education activities, they're based upon such a deceptive historical practice. It involves the National Academy of Sciences, it involves Science Journal, and prominent leaders in the radiation genetics community. That's our history, actually. The US EPA has served as an unwitting vehicle to implement such scientific deceptions due to its failure to both explore the historical foundations of cancer risk assessment, much of which occurred prior to its creation, and to take actions to correct these errors once the ramifications were understood. Thank you very much.
Thank you, Professor Calabrese. Well, I've got a number of questions coming out of that, around, I guess, a few different areas about the basis of a hormetic response, about your experience in uncovering these enormous flaws in your field and the foundations of it, and also about the broader context about the political situation, other decisions by the EPA. So with that overview, let me start with that last topic. You had said in your conclusion that the EPA was acted unwittingly in a way that misunderstood cancer risks. I think that if we look at other decisions like around DDT, where I believe there were studies that contradicted the decision that was made by the EPA on that, and it has quite the appearance of being a political discussion, the anti-nuclear ferment that arose, that these things have a connection to an overall anti-growth sort of paradigm that really began to take hold in the late 60s and into the 70s with things like the Club of Rome's book, The Limits to Growth, with the sense that we're going to need to reduce consumption. The National Security Study Memorandum 200, published in '74, which said that US policy should effectively be to prevent development in nations, or prevent population growth and development in certain nations that had resources of interest. To me, just with all of that in mind, I hear what you've gone through with this amazing story of scientific and fraud, if that's not too strong, sort of fraud, cover up, error. And I just got to ask, how do you see all of this fitting in a broader sort of anti-growth cultural paradigm that was taking hold, at least later in the period that you're discussing?
Well, I think that the area is complicated, and probably one group is using another group because of their findings, if it enhances their agenda. I think within this environmental domain, what really happened is that there was a manipulation of the country by leadership, certainly within the Rockefeller Foundation, that basically, could appear as though they were all above board, unless you look at the details. But what you have is when you basically create the rules of the game, and you can choose and pick who's going to make those decisions. You know what you can walk away and come back in 6 months, and you know what the score is going to be.
Right.
And I think that's what they did. They understood people's biases, and they knew what those biases were going to lead to. And even if you have people who are on that committee who might have been scientists, but who had either their own self-interest bias. So, but they're in effect very smart, but puppets in a bigger game of political intrigue, where somebody who knows what their decisions are sees where those decisions will ultimately fit into a major geopolitical decision making. So the person who is ultimately making this LNT recommendation may have no idea what's going on about international resource allocation, but the people who are the puppeteers, they actually understand what the rules of the game are and how to get to that by how they set up the pieces on the chessboard. And I think that the scientists in their own way are themselves big thinkers, but they might not necessarily be thinking in a major way. I think people like Mueller happen to be able to transform and go between both of those domains based upon looking at his role in geopolitical matters, what he's written, his role in the subsequent, pugwash meetings, and his influence on the international community with respect to the big questions, disarmament questions, relationships between the United States and the Soviet Union and others. Mueller had a big reach and a very broad reach.
In our in our last discussion, we talked a fair amount about what kind of reception you got with your colleagues and others as you started to realize that the foundations of understanding the dose response were wrong. I'd like to ask you about advice for young scientists today. I mean, let's say, you've got young researchers, or maybe even not so young, that are recognizing that there's something that's either being overlooked or that's wrong, a place where the general trend in scientific discussion is off somehow. What advice do you have about how to pursue that?
Well, that's actually the real ethical question. I mean, that's the tough question, because I'll tell you how it plays out today. And that is that my story actually resonates pretty well with people who actually follow the data. Yet actually it has very little traction within the scientific community, even if people write you cryptic notes, letters, talk to you privately, pat you on the back, encourage you, and this sort of thing. What young scientists and middle-aged scientists are mostly concerned with in the United States and probably other places is, guess what? The most important thing is the next grant you get. Can you get your grant funded? Can you get it renewed? That is all that counts. And if you think that the people who are in charge of this grants process may not be in support of a particular perspective, then you will not be associated with it. And so, for example, I know that if I walk into a room of young investigators, I can make them feel very uncomfortable, because they don't want to be associated with something that could perhaps upset their likelihood of getting funded. It's a very interesting thing. If you challenge the central paradigm, it's a very risky proposition. You keep your thoughts to yourself. You smile and shake hands. You just do the politically correct thing to enhance your career. If you are like me, I've been lucky. I was able to sustain funding for a long time and still have on my particular area of research. But this is a very unusual circumstance. I've been a very fortunate person to be able to do this. And so I don't know. I think that the real problem is ideological, and it's very high up, certainly in the United States, in terms of a political leadership within the power structure of funding agencies. And if you challenge this, then you challenge you challenge the way they basically think. I can tell you for sure, the latest National Academy Committee on Radiation, I did a FOIA on a number of these people. This is recent. And I learned that they had a discussion. And the discussion was whether they should cite any of Ed Calabrese's papers or not. And they decided not to.
Wow.
And then they had a discussion on whether to use the term hormesis or not. And then they decided not to. And so this is at the highest possible levels.
Wow.
This is not 1956. This is not 1972. This is 2022.
Wow.
This
Wow.
means it's happening now, and it's trying to constrain thoughts. It's trying to control things. It's trying to, if you challenge the status quo, then what they try to do is they try to find ways to emasculate you, to minimize you, to otherwise put you in your place. And for me, I don't really care. I'm too old, I'm too established, I'm too well known. I have my track record speaks for itself. If I were 35 years old, that might be a different story. I'm trying to make it. I'd probably, most people, they're thinking, I'll play the game, do what's in my personal best interest. And that's not in the best interest of society. It's in the best interest of you just trying to get my next grant. That's not the big question. It takes courage to challenge that. And I see that actually happening at the level of academic leadership throughout this country. They play the same game that the individual is playing, because they're working through their systems and they're hoping for more resources that go to their program. It's all about money. It's all about money, resources, and what enhances your career. And it has very little to do with the big picture and humanity and that sort of thing. It's not a good picture to paint. But I believe that this is a very significant issue.
So at the time that you realized that something was wrong here and that you needed to get to the bottom of it, what stage were you in? Were you already a professor at that point, or?
Yeah, I actually, when I decided to go forth on this, it was in a somewhat serious vein, was 1990. Okay, so 1990, I'm going to say I was 44 years old. Okay, and so I had made it. I was a full professor. I was doing okay. I had three lines of funding in my toxicology laboratory. That's just pretty good. But I'd have to tell you that I had experience with hormesis, and I wanted to understand more about it. And so I wanted to get some funding in that area. I wanted a fourth line of funding, but I wasn't sure just how significant it was. And so I organized a certain arrangement that would result ultimately in me getting about $200,000 to $300,000 a year to come into the University of Massachusetts for me to begin to develop my thinking in 1990 on hormesis. And so, yeah, but I was only going to devote about 5 to 10% of my time per week to that topic, because I had 3 other projects going on in my classes and everything. I mean, it's going to be busy. That's projects grow or they don't grow. And we'll see what happens after, X number of years. And after about the first 3 or 4 years, I tried to give my hormesis project away. It wasn't really gaining traction. And then what happened to me was in 1997, I got contacted by the Texas A&M University, and they had industry pass-through money, and they wanted to do an deep evaluation on chemical hormesis. And I had to go down there, visit, and so forth. I got a very large grant from them to start. And then because I had this chemical side grant, a person that I had a connection who was at National Nuclear NRC, Nuclear Regulatory Commission, wanted a parallel sort of a study on ionizing radiation. So then that grew. And then because of that, I ran other meetings, and then I was then funded by, the US military to do more. And within 2 years, I went from, a really small thing on hormesis to a gigantic thing on hormesis. And then I said, oh God, I have all this money and all this activity on hormesis, and I have these other projects that I'm working on. I actually, and I don't like to be a manager. I like to be a hands-on sort of a person.
Hmm.
So I really want to know everything that I do. And I said, I have to step away from those other. I think this is where the future is. The future's on this low dose stuff. Um, and so I actually phased down those other projects and decided, so that puts me around 54 years old or something like that. I said, I'm going to have to really make my move on this. And I decided to go in that direction. And so what happened was, and I got additional funding actually from the industry. And so I started moving in that direction. And but I was working on hormesis. I wasn't really attacking LNT. I was mostly trying to establish hormesis as an entity. And most people weren't taking me seriously. They, he's working on this low dose thing. Good luck to him and everything else, right? And so then what happened is that life changed for me in 2003, because in 2003 I got a paper published in the journal Nature, and they put me into their publicity package, and that was in February of 2003. And I got ended up getting all kinds of articles about me, the topic, and everything. And what that did was it was great. It gave me all this great publicity, but what it did was it frightened people. It frightened a lot of people because they could see, ooh, the implications of this. This means that this is going to challenge everything. If this thing hormesis takes off, it could challenge LNT, it could challenge this, it could challenge that. So soon thereafter, I started getting all kinds of opposition, all kinds of flack from almost every paper I would publish in a journal, got letters to the editor. I had opposing letters. It never happened before. There was an organized opposition against me, very organized.
Wow.
And so it started that way, and I knew that if I was going to be very successful, that this opposition would grow even stronger and more intense and very attacking. And over the next decade, the decade from my 55-year-old to 65-year-old, the intensity got progressively more and more serious. Where not only were they just writing letters to the editor and all that sort of thing, but people made strong moves to get me removed from my job.
Wow.
All kinds of claims, and I had to defend myself, and in pretty extreme situations. I would have to tell you, I'm still alive and well, and now 76 years old. But it's been it has never been an easy step, and even now, I'd have to say this past year, as a result of the last interview I did with you, as a result of that, it led to the Health Physics Society interviewing me and putting together a 22-episode documentary on cancer risk assessment and LNT. The 10 hours on YouTube, on their website. And I can tell you that the board of directors of the Health Physics Society, many of them, probably the majority of them, were totally strongly opposed to this, wanted this taken down.
Wow.
Wouldn't watch it, where anything you could say that was lacking, that was uncomplimentary about anything that I touched on it, in fact, people who offered the criticisms wouldn't even watch the videos, and yet it played to overwhelming support by people who watched it. And so I did 4 years on a number of people tied into the National Academy, this board, and others. And it's interesting to see in the modern culture, so to speak, how they scheme and connive and plan to neutralize you, to block your effectiveness. And I'm being kind right now. I'm being kind. There is the effort to get you fired. There is the effort to make all kinds of accusations about you, which you have to defend yourself on and survive. so when you are successful and you take on the establishment, they're powerful, they're connected, they're unseen, uh, and they know how to get at you, or they think they know how to get at you. And so, yeah, but I'll say it also makes life interesting. And when you go to sleep at night, you kind of feel good about yourself, actually. It's not actually a problem as far as I'm concerned. I say that I've learned a lot more as a result of this. I'm a much more experienced person in the ways of the world.
Hmm.
And also I've learned how to fight. I've learned how to defend myself, and I'm pretty good at it. And so, yeah, and I have a story to tell, and I'm still telling that story. So that's ultimately the bottom line, is that I'm still telling the story.
Hmm. That's great. That's great. So let me follow up with what your research has been on with hormesis. So you described this, during our talk today, is where, at very low doses, at lower doses, something that could be harmful at a higher dose could actually be beneficial. Let me ask earlier about the linear no threshold hypothesis. First off, am I right that this is essentially applied to carcinogens or things that cause genetic damage in particular?
Yeah, in general, that's how it historically has been used by regulatory agencies. There has been a movement in recent years to try to broaden the LNT to apply to non-carcinogenic
Hmm.
toxins, you might say, things like, let's say fine particulate matter. Some people have tried to apply it to lead, things of that nature. And I can tell you that I have copious amounts of literature on lead and hormesis. I haven't published a paper on it because I figured that if they can't handle what I'm publishing now, they can't handle if I have something on lead and hormesis. But I have things on every agent that's highly toxic. I mean, lead, yeah, I have a good amount. Methyl mercury, which is a very toxic neurotoxin agent. I have several dozen very good hormetic studies with that in neuronal systems. It's not, in neuronal systems.
Hmm.
And ricin, the very toxic agent that was used to try to kill let's say senators and others during the 20 years ago, after 9/11 and so forth. The most toxic element that people said that they knew. And you go into the literature, I have excellent studies with ricin and hormesis. Okay, ricin and hormesis.
Wow.
And so there's anything that can stress the system. This is the point. Anything that stresses the system actually defends itself. Like I'm defending myself against my challenges. The system, the biological system, if it's successful, will have evolved mechanisms that allow it to protect itself even against the most toxic chemicals. Because if it can't, it's not going to survive. The survivors will be selected for because of the biology that they have evolved that allow them to cope with these different stresses. So yes, and then it's within that framework that the theoretical and evolutionary basis of hormesis emerges.
So for these hormetic responses, it sounds like you've got a lot of observational data that at these hormetic doses, there's a benefit. For a lot of these things, do you have much, what's the idea about how this happens? Like how detailed would you say the field is in understanding the mechanism of what's bringing about the hormetic effect?
Well, I have to tell you that I've been hot on this for a long time, let's say over 30 years. And I have worked on this for probably 70 or 80 hours a week, technically.
Wow.
For 52 weeks of the year for 30 years. I mean, that's what I do. This is what I do, right? And I have to say that the first 10 years, I spent my time trying to just prove that it existed, right? And so in the early 2000s, the scientific community demands more from you And they said, well, just because you can show that it exists and it's reproducible and all this, you're still not going to get published. You have to show us the mechanism. We worship at the altar of mechanism. I said, well, okay, that's fair enough. And so over the last 20 years or so, the evidence on hormesis has become quite comparable to any field in the biomedical world, toxicology, pharmacology, you name it. And it's all about observations that you then have mechanisms for, and pathways and receptors and whatever else the details of those are. And I know that just as an example, in 2013, I published a paper of 400 different hormetic dose responses where I actually had the mechanism down to the level of receptor and cell signaling pathway, over 400.
Wow.
I mean, that would have several thousand today. You know, it's all, I don't even have to try it because all the investigators, that's how they get their papers published today too. They have to do that extra amount of work to show it. So, and so hormesis is, if somebody doubts hormesis to me in conversation, it tells me that they don't know the literature. It tells me that they are totally ignorant, to be honest with you, because there's just today in the PubMed, just today, every day, every morning, so I come downstairs, I check my email, and the very next thing I check is PubMed, and I type in hormesis or hormetic, and I want to see what's new today, any new paper listed. So today in PubMed, there were 4 new papers on hormesis, okay, in 4 different areas, one on plants, one in microorganisms, one on cannabinoids, one on something else, and they're all citing me. I have to say, they all cite my work, and they're all mechanistically oriented. And so last year, when I went back in the 1980s, in Web of Science database, which is a gigantic database, they cited hormesis or hormetic about 15 times per year. Okay, last year in the same database, they were cited was more than 19,000 times. Okay, it's gone from 15 to more than 19,000 in 1 year. So the concept of hormesis has greatly expanded, and even with over 19,000, most of the biomedical community is still ignorant, but it's a lot less ignorant than it was, and it's in a lot of different areas. It's growing very rapidly, and so you can't kill an idea if it's real. And
Right.
so, yeah, and for me, I'm just one person now. These are all these people all around the world who are seeing it and using it. If it helps them build a better mousetrap, they'll use it. And that's what's actually happening. It's not that they believe me. It's helping them explain their system better. And that's why it's actually working. So it's the way it should be.
So, in terms of the kinds of other benefits that could come from that, it seems like there's potential treatments in the works. Could you say anything about, hormetic-based treatments? And also, I feel like this would be a good time because it's going to come up in people's minds to differentiate this from homeopathy.
Yeah, I'll try to show you where people are experiencing it right now, for example, and then we can go into homeopathy and things like that. But this is interesting. This is the most important thing to realize, and that is that if you're trying to improve biological performance, and that could mean anything like growing hair, it could mean protecting your skin from ultraviolet rays, it could mean extending your life, it could be protecting yourself from having a heart attack or damage from a heart attack, same from a stroke and so forth. It could be improving your memory. All these so many different things, right, that are important to people. Now, reducing stress, reducing all kinds of problems, let's say with seizures and anything that people could experience. Well, what I did was this is interesting. I looked into all the preclinical literature. These are like the mice and rat studies before they go to test them on people, right? If you I looked at all these anti-anxiety drugs, they call them anxiolytic drugs, the drugs that reduce anxiety. and there are a lot of people who are taking lots of anti-anxiety drugs in the United States every day, right? Okay. And you may say, well, okay, that's great. They must have been tested in people in clinical trials. Yeah, they've been approved. But they were actually tested first in mice and rats, all right, for the most part. And so, well, yeah, they actually test them there, and they have ways to figure out how do they reduce anxiety in a mouse or rat. And so now the interesting thing that they do is that they have a broad dose response relationship. They might test them with 4 or 5 or 6 or 7 doses, something like this. And what inevitably in all the studies that I went after, because I looked at maybe 200 different chemicals, okay, anti-anxiety chemicals, a lot of chemicals. Every one of those studies, they showed a hormetic dose response, that the optimum was the biggest decrease in anxiety in these animal models. It showed this inverted U-shaped hormetic dose response, and the magnitude of the increase was approximately only 30 to 60%. That's how much it was. But what happens is, and I did the same thing for anti-seizure drugs, and I did the same thing for memory drugs. I went through a whole series of these drugs. They all showed a hormetic dose response, and they're all increased by about 30 to 60%, right? Now, the pharmaceutical company, they take the one concentration that's optimal, or maybe 2 that's in that optimal zone, and that's what they test within their clinical trial to see if it'll work. And then if it works, then it goes to the FDA and they go through that whole process. But the point that I'm trying to make is that all these different drugs that are already been approved, they're already out there that people are taking, those drugs are, guess what? They are based on what? My concept of hormesis, because all that human data comes from what? It comes initially from a hormetic study, the optimal dose in a mouse or rat study, or whatever model that they're working with. And this and that's the same thing for hair growth and everything else that I have looked at. It's pretty massive. And so in terms of, so right now, even though the world doesn't understand this, the world is using my concept of hormesis in many different drugs that are being used. And I can also tell you that sometimes the hormesis concept is not beneficial for us. It's beneficial for the creature or the system that gets it. So say back in 1945, this is interesting here. Penicillin was just becoming big in 1945. And so people decided, and this is the US FDA, decided to take a low dose of penicillin, and they gave it to very harmful bacteria and gave it to mice. Now, penicillin at a certain dose will kill the harmful bacteria and so forth. But at low doses, it actually stimulates the proliferation of the mice. And so when they gave a very low dose of penicillin with the harmful bacteria to the mice, and what it did was it made all these mice die.
Wow.
It stimulated them to reproduce, and that killed the mice. As the dose went up, what happened is it prevented the mice from reproducing and the bacteria from reproducing, and the mice all lived. And so they called it a hormetic dose response in 1945 by the US FDA, and that was how penicillin worked. And so at low doses, the antibiotic actually stimulates the organism that it's trying to kill to proliferate. And at high doses, it actually inhibits it. It's this hormetic sort of a dose response. The same thing happened then to streptomycin and a series of these antibiotics. It was very, very significantly based on dose. Then in the first decade of the 20th of the current millennium, I got a very large data set from the US National Cancer Institute. It had several thousand drugs and so forth, and they're anti-tumor drugs, so they're supposed to, prevent tumor cells from reproducing and so forth. I'm saying, okay, I bet you most of these drugs that are designed to kill tumor cells, I bet you they stimulate the tumor cell to grow at low concentrations. And so I got their data, and they have 4 or 5 or 6 doses, whatever they have that are being tested. And I got their data set, and sure enough, when you look at them, I find that at low doses, the predominant number of these showed a low dose stimulation, and then at high doses, they did what they're supposed to do. You want them to do, they inhibit it. And,
Wow.
and so, and then I said, well, what are the implications of this? Well, if you have a drug that has a long half-life in your body, 30 days or something like that, you could be into a low dose zone for a long time before it gets out of your body. And
Right.
you're being treated for this cancer, and it's causing the cancer to explode in your body.
Wow. Wow.
And so I look at, hormesis as one of these things that you have to understand what this is and what it means, because you have to have it work for you and not work against you. And so it's not always going to be, giving you a benefit. It may be benefiting the thing that you're trying to fight against. And so you have to understand how all that fits together. But the interesting thing here too is that it deals with an increase of about 30 to 60%. And so a lot of people today would like to live forever, right? And so people take supplements and they exercise, they do whatever they can do to live in to make it into a blue zone or something like this, right? Want to make it to live to be 100, live to be 105 or whatever. How long can one live if you could maximize it out? And so a lot of work has been done on this, right? But they, you can't study mice and rats because they live for 3 years or whatever it is. It takes too long. So they tend to study the little nematodes that live for about 20 days, and they study fruit flies that live for about 20 to 30 days, and some other little, shark creatures, but that they know an awful lot about, an awful lot. They know their genetics, they make all these mutants, they do all these very interesting things. But the mouse studies and so forth are very, very, limited because they're just too expensive and take too long. But I've looked at several hundred different chemicals that have been tested with these agents and that extend longevity. They extend lifespan. They clearly do. They have underlying mechanisms. The mechanisms parallel what goes on in the human population. Guess what? They live no more than, they all show a hormetic dose response. At low doses, they stimulate. High doses, too much. It actually makes it counterproductive. They extend their life by about 30 to 60%. It's the hormetic principle.
Wow.
The
Wow.
hormetic principle. That hormesis controls and directs everything biomedical that we have. It just so happens that I've studied this for 30 years, 52 weeks of the year, all those hours of every single day. This is what I do. At some point in time, the world's going to catch up and see it. And they haven't. Some have, obviously. Some probably have gone beyond me. But this is what I do all the time, and it's just waiting for people to catch up. And everything that I do within my life is tied into activating hormetic mechanisms under low-level stress to enhance my adaptive capacities. That's what I do. That's what I try. I have a job that allows me to try to figure out how I can get that extra 30 to 60% of my longevity, right? Yeah. But and there's a lot that you can do that in fact could enhance your capacity to live, as they say, a healthier lifespan and a longer lifespan. So combining those two, but it's all based upon understanding of hormesis. And once at some point, I would like to think that the public health community and the medical community would actually understand this and to see how it takes place. But I just know from the way this is expanding within the scientific community that times on, the science is on my side. It's just a matter of time till it all comes this way.
Has the pushback and attacks that you've gotten, have they had a hormetic effect on you?
Oh, boy, yeah. I'd have to, well, I'd have to say that it's when you're not sure whether you're losing your job or not, that's a high level of stress.
Okay.
So that's probably in the beyond the hormetic stress, put it that way. And so I've gone through some of those, and those aren't really good to go through. So you have to kind of fight your way through that and just realize that it's only going to last 6 months or 9 months until you're in or out. One way or the other, you are in or out. But I'd have to say that everything that I do is designed to stress my system. And I'm putting myself into mostly an adaptive condition. And I might do this for example, on, let's say, on dietary intermittent fasting. I eat one meal a day and I go 23 hours without eating. Okay. And so I do that. I exercise every day hard for an hour, aerobic. I take, I take a whole series of dietary supplements, many of which I've written papers on and published on the scientific literature on their hormetic benefits. And once I do that, then I kind of can optimize what my dose might be. So I'm constructing what I think is my optimized hormetic way. And I've learned and grown, and it's all based upon the pharmacokinetics and their mechanism and their tissue distribution and what I'm trying to work on. So I'm actually trying to do that, and I don't think that too many people, have that luxury of a job that but in terms of me, the anxiety towards me on hormesis is, in fact, if I were to focus just on things that promote life, in the terms of, curcumin or ginkgo biloba or ginseng or ferulic acid, or eating broccoli or whatever you want to call it, or the things, and people don't seem to get hot about that. If I were to write about it, and people probably like that because they can learn and that can enhance their life. If I were to write a paper on the hormetic effects of lead or cadmium or methylmercury or PFAS, or they all have lots of hormesis, I would say, right? They all do. I know they do.
Huh. Then
that freaks people out in the environmental world, because you're challenging, something within their bailiwick. But it's all hormetic, and it depends on what I'm particularly interested in. And what I'll do. I've done a lot on different pollutants for sure, and the like. But I do a lot on what I call phytomedical extracts. Things that I take as supplements. I'm interested in myself getting that 30 to 60%, and so I'm interested in what's the next supplement that I want to take. And how does it relate to all the other supplements I take? But I'm sitting on a very large stash of hormetic studies that I have preliminary analyses of, all on PFAS, the big PFAS that rules the country in terms of environmental cleanups and all this. And I haven't published it yet, but I have a massive amount of information on hormesis and PFAS. Now, whether I get around to doing that analysis and publishing it and so forth. But if I do, I can guarantee you that there would be probably 50 people in the environmental world that would just freak out. Maybe 1,050 that would freak out. And
good.
And they're just waiting for what's he going to do next? What's he going to do next? They don't really know what I'm going to do next. And I don't know what I'm going to do next. It depends on me, right? But I'm mostly trying to extend, help people extend their health span and their lifespan. And that's really what I'm mostly interested in.
Great. Well, I hope I'm able to work 80 hours a week like you when I'm set in my mid 70s.
Well, I have to go and have a tough workout after you've worked me out for 3.5 years. That's where I'll be going. Yeah, I'll be going there right now. Yeah.
Okay. Yeah. All right. Well, this was a lot of fun. Thanks a lot. Because you made a discovery, right? I mean, you had one view, and then later you had a different view. Something changed in your mind. That's very important. A new idea developed, and that.
Yeah, actually, there was a lot of those individual things. This idea of the 30 to 60% was a new discovery. Actually, was a discovery. And, you're going through, and I think I have the mechanism for hormesis. That's like a discovery. I've got a lot of individual discoveries on this, and
Let me ask on that. So are there phenomena that you're running into or like empirical generalizations you're able to make for which there really isn't a compelling mechanical explanation, and maybe that might hint at an opportunity for biology to make a significant breakthrough?
well, there's always more complexity. You think you've explained it, and then there's some, and what I think happens is that you have a model, everything's a model, but how generalized is it? And is this the strategy that this cell used? And there may be a complexity of how different cells in different organisms, they may have a basic pattern, but in the end, they probably have had to figure out their own way to modify it and morph it for their own ecological setting to make it work. And so there's a lot of complexity, within how to do it. Not every cell in every organism doesn't act exactly the same. They might have the same basic strategy, but to actually figure out how they're playing this out in precise terms is what people spend a lot of time. That's why they work with these nematodes. They have the same basic patterns that we do. They really do.
Hmm.
But how it actually plays out exactly in me and exactly in you, nobody can quite truly know. That sort of thing. It's difficult. Even now, and the hard thing now is that I pretty much know what's happening, I think, but I don't know, for example, I take 35 to 40 supplements a day. But I'm trying to not make myself intoxicated, and I'm trying to be helpful. And I don't know how all this mixture, this 35 to 40 things, this all at one time is working, because when they're studied individually.
Right.
And I'm trying to figure out, and I can't wait for the FDA to ever figure it out, because they'll never figure it out. They won't even come up with a question to figure it out. And so I'm trying to find a way to maximize my health in light of all my knowledge, and realizing that it's a lot imperfect, because we live off of these a lot of knowledge, but a lot of intuition is driving our knowledge here. It's a bit like, the art of medicine. It's the art of medicine. There's a lot of science, but there's a lot of judgment. And I'm not sure, how all this gets translated into the world of life in the United States, then through the FDA. There's the one thing that's good is that, we're educated, we have access to information. If we can then decide what we want to buy and take and self-medicate, I think that's kind of where it is these days. I mean, I don't think we're gonna, get the decision from outside ourselves. And so if you're really well trained, you might be able to be helpful to yourself. It's very liberating at the same time. I mean, man, I'm just in search for all that sort of thing and enjoying it. You know what I mean? Along those lines. I present a crazy picture to the outside world, I'm sure.
I think it's a pretty good picture.
Well, I'd like to thank you. This is you put so much time with me today, 4 hours. That's more than anyone could ever tolerate. But if I can be help when and if you have any questions, let me know, that sort of thing. And we gave it a good shot, got most of it all in, and had things that no other interview has ever had. I'm sure of that. And some things I spent too much time on some things and didn't include some other things, but the course of it all, we kind of covered it all.
Yeah.
And did the best we could possibly do. If anybody's really interested, this is a very unique thing. It'll be a very unique interview for those who are LNT You know, they just are sucked into that, or they're interested in the hormesis thing, or they like to listen to my stories. They will be, this is a unique thing. This is a unique interview. Nothing is like this one before. So, and it started off very interesting, I think, and it ended very interesting. And in between, there's a lot that's there. For those who want to go after it, there's a lot that's there.
Yes.
Yeah, so thank you so much. And have to thank Rick for connecting us again, which is good. And thank him again for me.
Okay.
Okay. And you have a wonderful rest of the afternoon.
All right. Enjoy your workout.
Nice to see you. That's where I'm headed right now.
Okay.
Tough
Great.
out on the bike. See ya.
Thanks a lot. Thanks a lot.